Hello, and welcome to the full course session on Strength of Materials Engineering Basics, your gateway to mastering the fundamental principles of material behavior under stress and strain. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're committed to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on strength of materials and other essential engineering concepts. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll begin with stresses and strains, exploring Hooke's law and stress-strain diagrams. You'll gain a thorough understanding of material properties such as stiffness and Young's modulus, as well as how to interpret stress-strain graphs. We'll also introduce Poisson's ratio and shear stress-strain relationships, helping you analyze material deformation under various forces. In the second chapter, we'll cover principal stresses and principal planes. We'll dive into Mohr's circle of stresses, plane stress transformation, and the general equations used for plane stress transformations. You'll learn how to determine principal stresses and maximum in-plane shear stress using Mohr's circle, which is a critical tool in material analysis. In the third chapter, we'll explore shear force and bending moment in beams. You'll learn about the bending and shear stresses in beams, torsion in circular shafts, and internal forces. We'll break down beam supports, loads, and introduce shear force diagrams as well as bending moment diagrams. We'll also cover bending, deflection, and torsional deformation in circular shafts, along with the torsion formula. In the fourth chapter, we'll focus on the theories of failure. You'll learn about failure by yielding and fracture in materials, with an emphasis on the behavior of ductile and brittle materials. We'll introduce yield criteria for ductile materials and failure criteria for brittle materials, providing you with a strong foundation in understanding material failure. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with Strength of Materials Engineering Basics.
Welcome to the Strength of Materials course. We are in the first week of this course. So the first week is all about mechanical properties of engineering materials. Mechanical properties are physical properties that are exhibited by the materials upon the application of forces on them. We will also focus on strength of a material, wherein strength of a material is its ability to resist loads without breaking or deforming excessively. We will also see how to quantify it and the different measurement methods. In this session, we will be looking at the following topics. Our session starts with strength of materials, definition for strength of materials, and then we'll look into the basics of strength of materials. We'll go through simple stresses and simple strains. We'll establish the definition for stiffness of materials. Later, we'll go through material properties. We'll establish a connection between load deformation diagram, which is basically stiffness, with material properties, and stress and strain diagram, which is basically Young's modulus with the material properties. Next, we'll understand how to read stress strain graphs. Then we'll see about Poisson's ratio and then end our session with shear stress and strain. The learning objectives for this session is that we'll first try to understand the mechanical behavior of materials in engineering sense, which is very important. We'll then try to define the term strength of a material. We'll use this term as we progress with the course. Then we'll try to understand the types of simple stresses. So these simple stresses that can be applied on the structural elements. Next, we'll try to understand the term strain, which is basically how materials deform under stress. Next, we'll try to establish a relation between stress and strain, which is the Young's modulus, and we'll also work through some problems. Finally, we'll try to end the session with an overview of Poisson's ratio and shear stress and strain. What is strength of material? Strength of a material is a major factor during the selection of materials for engineering purposes. It is the capacity of a material to carry or resist loads. For example, an ant can lift 10 to 15 times its own weight. Some species like the Asian beaver ant can even lift up to 100 times its own weight. So an ant can be said to have such high strength. Sparing the above said example, usually loads can be of different types. They are tensile, shear, flexure or torsional loads. Since we are engineers, we are more interested in the strength of a material in engineering terms. In engineering terms, it is a calculation of stress and strain in structural components. The strength of a material is affected by two major factors. First are the mechanical properties of the material. These are the properties that involve a reaction to an applied load. Second are geometrical properties. These are derived from the geometry of a solid body or particle. So basically these are derived from the properties that are affected by shape and size. Now coming to some of the important mechanical properties, the first one would be strength. Strength of a material is its ability to withstand an applied load without failure or excessive plastic deformation. Next is stiffness. Stiffness is the ability of a material to resist deformation. Toughness is the amount of energy per unit volume that a material can absorb before rupturing. Finally, hardness is defined as a material's ability to withstand localized permanent deformation. Next, let's look at geometrical properties. The first property is volume. The strength of a material increases either when the structure is very small or when only a small volume is under strain. So a smaller sized material is stronger relative to its volume. However, strength is also dependent on other factors like orientation of the material. Example, material with higher length, weight and thickness has higher strength. These are the dimensions like length, width and thickness of the material. Then we have boundary conditions. Boundary conditions can also be called as boundary constraints. So this is the way the material is supported before a load is applied on it. Finally, we have changes in the geometry, which is the changes that a material undergo due to load applied or environmental effects. Here also the strength of a material can also change. So for this, as an example, the cross section of a steel rod in tension reduces and thus reduces the amount of strength the rod can take. Now let us look at simple stresses. Stress is the intensity of a force on a solid. Let's start with the basic type of stresses that are found in materials when they are under a load. To understand simple stresses, one of the simplest types of loads that can be applied on an object is tensile loading. Let's consider a uniform cylinder that is pulled apart by a force applied on the either ends. The thickness of the cylinder will get reduced at the center and the material will eventually break apart. The force that is applied on the cylinder is F, depicted in kilonewtons, and A is the cross-sectional area. Stress, which is sigma, is equal to F divided by the cross-sectional area A. Thus, stress is affected by the force and area. Higher force applied on the material implies that there is a higher stress on the material, and when cross-sectional area is higher, the stress on the material is lower since area is inversely proportional to stress. Thus, in this case, the stress on object A, which will be higher than, thus in this case, the stress for the object which has lower cross-sectional area will be higher than on the object which has higher cross-sectional area, but provided all the other conditions remain the same. Commonly used units of measurement for stress are kilonewton per meter square or Pascal. 1 megapascal is 1 MPa, which is equal to 1000 kilonewton per meter square. Another unit of measurement for stress is pounds per square inch or PSI. 1 megapascal is approximately equal to 145 PSI. Let's look at the difference between engineering stress and true stress. Engineering stress, that's sigma E, is equal to the applied load divided by the original cross section of the material. However, when a material is placed in tension, it shows a necking behavior, that is, the cross sectional area is reduced when it is under stress. This reduction continues as long as the material continues to be under stress. Thus, in reality, a different stress needs to be measured. This stress is called true stress or sigma T as given here. So true stress is the applied load divided by the actual cross-sectional area A1 of the material. A1 is the changing area with time. Therefore, sigma T is calculated using the instantaneous change in area during the tensile test. Since A1 is always less than A during the test, the true stress is greater than the engineering stress. Sigma E or engineering stress is considered to be the average stress in the system. This is also called as nominal stress. However, it is very difficult to measure A1 as the test is being conducted. Thus, to simplify, we use A. Hence, we always calculate the engineering stress. Now, let us look at the types of stresses that can act on a body. First is normal stress. This stress acts along the direction of the force or the transverse direction. The first kind of stress is tensile stress. This is a stress that pulls apart an object. When under a tensile stress, the object will distort, that is, its dimensions and shape will change. An object under tension will elongate and undergo necking. And here, necking is the phenomenon where the cross-sectional area reduces. As this stress is increased, the material will break apart. The next type of stress is compressive stress. This is also a normal stress. Here the force acts along the direction of the material. Compressive forces push the material together and an object under compression will become shorter and begin to bolt. That is, the sides will distort by curving outwards and begin to bulge. This bulged portion will then break off as the load continues to be applied. The deformation caused by normal stress is always along the direction of the force. Normal stress is equal to force divided by the cross-sectional area of the material, as we discussed earlier. In the case of tensile forces, the object will elongate and reduce in cross-sectional area and eventually break. While in the case of compression, the material will become shorter and increase in cross-section area and eventually break. In both cases, the deformation occurs along the line of the force. The next type of stress is called as shear stress. Shear stress acts perpendicular to the material, that is in the longitudinal direction. It causes slippage along the planes parallel to the stress. Shear stress is depicted using tau, which is equal to the force divided by the cross-sectional area of the material. An object under shearing will bend and eventually break. The next type of force is torsion. Torsion is a twisting motion that is applied due to torque. It is a rotating moment that translates to shear stress. Thus, torsion is twisting or wrenching of a body by the exertion of forces that tend to turn one end or part along the longitudinal axis. As seen in this figure, the graphical representation shows us torsion. Here, the torsion is shown in violet and the radius in red. The force is in blue. So when a torque, which is a rotational equivalent of a linear force, is applied on a body, it twists as shown in the figure. Next figure shows us how the material is twisted. Now let's look at simple strains. Strain is the byproduct of stress being applied to an object, which can also be told as the physical manifestation of stress on an object. Similar to stresses, there are various kinds of strains. Now let's discuss simple strains. Strain is the measure of deformation due to loads. In simple terms, it is a measure of how much deformation occurs in an object when it is placed under a load. Let us assume a material which has an initial length of L0 or original length. This material is placed under a tensile force of F. Under this force, the material will elongate to L, which is the final length, and here L is equal to L0, which is the original length, plus delta L, which is the change in length. Thus, strain can be defined as the ratio of change in length to the original length. That is, it is a measure of amount of change in length with load. Strain can thus be defined as epsilon, which is equal to delta L, that is change in length, divided by L0, which is the original length. Since both delta L and L has the same units, it is a dimensionless unit. Now let us see the difference between engineering strain and true strain. Similar to engineering stress, we also have engineering strain, which is epsilon E. It is the elongation delta L divided by the original length or L0 of the material. When an object is placed in tension, it shows a necking behavior. That is, the cross section is reduced when it is stressed. This reduction continues as the material continues to be under stress. Thus, in reality, a difference strain needs to be measured. This difference strain that has to be measured is called as true strain, or can also be denoted as epsilon t, which is delta L divided by L1. L1 is the changing length with time of the material. Epsilon t, or true strain, is calculated using the instantaneous change in length during the tensile test, which is L1. Since L1 is always lesser than L0, epsilon t is always greater than epsilon e. Thus, true strain is lesser than engineering strain. Since it is very difficult to measure L1, we use engineering strain as the nominal measurement unit. Strains can also be classified based on the loading type. The first type of loading is tensile loading. In case of tensile loading, delta L is the amount of elongation. Thus, tensile strain is equal to the elongation delta L divided by the original length L0. Also, tensile strain is always positive. The next type of loading is compressive loading. In this case, delta L is the amount of shortening of the object. Thus, compressive strain is the reduction in length delta L divided by the original length L0. In the case of compressive loading, the compressive strain is negative. This is due to the reduction in length of the object. The next type of loading is shear loading. In the case of shear loading or shear strain, the object deforms in the longitudinal direction. Thus, delta L is the amount of bending shear strain. Therefore, it is the amount of bending delta L divided by L0, which is the original length of the object. Then we have volumetric strain. Volumetric strain is the ratio of change in volume to the original volume of the material divided by V0, which is the original strain of the material. Volumetric strain is equal to sum of strain in all directions. Thus, volumetric strain is equal to 3 times the linear strain that is on the material. Strain can also be classified based on the direction of deformation. Let us assume a material which has an initial length of L0 and an initial weight of B0. When this material is placed under a tensile load, it will reduce in cross section. This reduction is delta B. It will also elongate this. Elongation is delta L. Thus, the transverse strain, which is normal to the loading direction, is equal to delta V, which is the reduction in weight divided by B0, which is the original weight. Similarly, longitudinal strain is parallel to the loading direction. Thus, longitudinal strain is equal to delta L, which is elongation divided by L0, which is the original length. Now we can see some of the elastic behavior of materials. When it comes to mechanics of materials, countless number of scholars have made notable contributions in the field. The very important ones are elastic stiffness, which was given by Robert Hooke, who did the spring mass test. Then we have the material properties that was first introduced by Thomas Young, in which the first property being Young's modulus in 1810. Then we have the Poisson's ratio, which was introduced by Simon Poisson. First we'll start with the material properties and load deformation diagram, which is basically stiffness. Robert Hooke first introduced stiffness in 1648. The primary definition of material stiffness was provided by Robert Hooke, and his experimental method involved suspending a number of springs with masses measuring the deflection and respective extension. The diagram which you can see in the right side is an example of one of the systems that Robert Hooke presented. So in his experiment, he had a spring and a mass attached to the spring, and he calculated the deflection of that spring and how much is extending because of the mass. The force and the spring's extension are proportional to each other. So if we have a force on the mass, there will be an extension and then the spring will start extending. However, if we have an external force on it, the force will make the spring elongate, and elongation is directly proportional to the force that is applied. That was the experiment that Robert Hooke did. So when he suspended the mass and then put a load on it, he established the graph which is known as the load versus extension graph or load versus deflection graph. And he realized that the load is directly proportional to the extension of the system, or the extension is directly proportional to the load. So with the increase in load, extension linearly increases until a point which is known as the limit of proportionality, after which the linearity of the load extension graph goes away. And then we have a non-linear relationship. So basically the material goes into the non-linear field. So the elastic behavior of the material was first introduced by Robert Hooke, who said that there is a certain limit till which the material behaves elastically, and then after that the material stops behaving elastically. This is called as the Hooke's law. But after this material would experience plastic behavior. So from Hooke's finding, we can summarize that within the elastic limit, W is equal to K times U, which is the axial stiffness. Therefore, K is equal to W by U. And here K depends upon material properties and the geometry of the bar. Let's see an example to understand the K value for a system. In this problem, as you can see, a specimen with the diameter 13 mm and gauge length of 55 mm was tested under tensile loading, and the load versus elongation data is given. This data is ideally found in any experiment that is performed on the instrument or on the universal testing machine. So the load and elongation data is given, and we have to determine the stiffness of the material, which is the axial stiffness. We will use Excel to plot the graph, and then we will see how we can find the axial stiffness. The given graph here is the plot of the table we saw in the example question. In the graph, we can see that units for load and elongation are given as kilonewton and millimeter respectively, which is a very important information to note. We can also see that the linear climb is followed by a non-linear curve in the later stage of the plot. For better understanding, let us restrict our value of load till 41.9 kilonewton. This way we can concentrate on the linear range of the problem. After this line, the linearity has stopped, which means it has moved from linear to non-linear at that point. So we can say that this is the point where proportionality constant is met. K value is no longer linear or is the point of proportionality, which we have seen in the graph as well. Hence, this is our limit of proportionality. Now we have to find the stiffness. Stiffness is nothing but the slope of the line of that linear region. To find the slope, we divide the load by the elongation, which is finally the formula to find stiffness, as we saw earlier. In this picture, we can see that the limit of proportionality is marked and the slope is actually calculated using formula for K. Now it should be noted that the K value is true only under the limit of proportionality. That means that any value that we get after load limit 35 kilonewton as per the plot does not fall under our range of stiffness. By this, the highest value of stiffness is for load value 12.1 kilonewton, which is 654.01 kilonewton per millimeter, and this is our final value of stiffness 2. We look into material properties and stress strain diagram, which was introduced by Thomas Young and which gives us one of the most vital material properties known as Young's modulus. Young's modulus is a theory that defines if a material is within the plastic limit or outside the elastic limit. So Thomas Young did these experiments in 1810 and developed the theory of elastic deformation of materials. He was the person who discovered Young's modulus, the tensile test currently performed on any system that has become a very important experimental test. It helps in determining the Young's modulus along with other material properties and possible failure. The picture which you can see on the right side is an ideal example of a testing rig that is used in performing the tensile test. It is mounted on a universal testing machine, as you can see, and then the specimen is pulled. These are some of the examples of dog bone structures for rods. However, different analysts have different ways of doing this type of a test. Usually, the dog bone test is carried out only when there is availability, and in most cases the labs that perform these tests do them using the rectangular shaped simple specimens. Other than that, we can also find cylinder shaped specimens for which the grips are different when compared to the ones for rectangular ones. For samples and accessories, material samples are tested in a variety of geometries. However, with availability, the most common one is the dog bone structure. Several techniques are used for measuring the dimensional changes in the structure being tested accurately. The devices that are shown here, in which one being the strain gauge, which is usually mounted on the specimen, and the other one is a non-contact extensometer, which usually uses quality of video imaging capability to capture the movement of the material when it is pulled apart. Now let us see some equations that are used to calculate stress and strain. We have already come across these equations, but to make it clear, we will go through them again. In this, we can already see that the gauge length is given. Considering the load extension behavior of materials, Young converted them into stress strain data. Engineering stress and strain are calculated based on the sample cross section as sigma is equal to internal normal force divided by the original cross sectional area, and that can be denoted as P divided by A naught. Same way, epsilon, which is the strain, is equal to change in length divided by the original length, which is denoted as U divided by L naught. These are equations from whatever we saw earlier. And we also saw that we usually do not consider true strain and stress for normal problems due to their inconsistency. But instead, we use these equations to keep the true strain and stress in our calculations intact. So, how does an ideal stress strain diagram look like? Here, in the given figure, the true and engineering stress and strain are shown for a steel specimen that is loaded to its failure. So, as you can see in this graph, there are two curves that run throughout. In the linear region, the graph doesn't change a bit, but only after a certain point that the graph starts to move up by a certain distance. So this movement, which is going up, as you can see in the figure, is known as the true stress strain data. So this is how the material is supposed to behave without any other aspects. However, when it comes to engineering, we as engineers like to keep things safe, and therefore to keep things safe, we make a new graph which is known as the engineering stress strain graph. And this engineering stress strain graph has your ultimate stress as the highest stress, and fracture stress is usually lower than the ultimate stress. However, in the actual stress strain graph, which is the true graph, as you can see in the figure, the fracture is actually higher, or we can say way higher than the ultimate stress, but the engineering stress strain graph is usually good enough for us. Next, we can see that the graph is divided into two major regions, which is the elastic region and the second one is the plastic region. In the elastic region, material has an elastic behavior, whereas in the plastic region, the material has a plastic behavior. Again, this plastic region is divided into four parts. We also should have this in mind that the plastic region is specifically for ductile materials. The four parts that is divided is for ductile materials and not for brittle materials. Also, we don't have this big a stress strain diagram in the tensile region. In the initial stages, we have the yielding process, then we experience strain hardening. Finally, we finish this with the necking, and that is the region where the material keeps breaking. The highlighted region which you see in the diagram, which is red in color, is where all the elastic limit samples are present and all the elastic limit calculations are done. So now this region gives us the entire linear relationship between the samples, which is used in the majority of the calculations. We have a few points here which will be introduced later as we go on further. So on the left side of the graph, the first point, which is sigma prime F, is basically the fracture stress. The next point, which is sigma U, is the ultimate tensile strength and is the highest stress when it comes to engineering data. However, for the true scale, it is completely different. Then we have sigma f, which is for fracture, but this sigma is not that critical to find. But we need to understand that sigma y is when the material is trying to yield. And then we have sigma PL, which is when the material is in the plastic region. Now we can see that elastic region has the elastic behavior and the plastic region has the plastic behavior. And due to this, yielding, strain hardening and all those steps finally come to a place where the material failing happens. One important thing to understand is that inside the plastic region, the deformation that is happening to the system is permanent and cannot be changed. Whereas when it happens in the elastic region, the deformation is recoverable and it can be changed, which can also be called as it can be cured. Some important points to be noted here is that Young observed that the sigma epsilon slope was constant for any material independent of the sample geometry. This should be same for any homogeneous material system. Also, there is very little difference between engineering stress and true stress. We can tell this from the diagram, as we can see that the difference in the graph only starts from the strain hardening region and deviates a little bit from there. Hence, there is very little difference, and this difference comes into play only when designing purpose is involved. We have to make sure that the material is safe enough, the design is safe enough, and understand the different materials we have in different ways. So with that information, Young found this derivation on his name, which is Young's derivation. His derivation made sure that the stress strain slope for a particular material was observed to be constant and was independent of the sample geometry. This is true and should be same for all homogeneous material. A good indication of understanding the fabrication of composite material is having a near constant sigma epsilon slope when tested at different locations. These observations led to the definition of modulus of elasticity, or Young's modulus, which is represented by capital E. And it has a similar graph to what we saw for stiffness. However, the x and y axis are changed here. It is plotted against stress and strain and not against load and elongation. For uniaxial loading, we will note that sigma is equal to E times epsilon, or E is equal to sigma divided by epsilon. Below here, we can see some metric properties that are standard for various materials. Mild steel has a Young's modulus of 210 gigapascal, while aluminium has only 70 gigapascal as its Young's modulus. As we go on, the most lowest Young's modulus value is for rubber, which is 0.04 gigapascal. So therefore, we can say that mild steel has better performance in the elastic region, whereas rubber is not that high, which makes it a very bad material to be used during building constructions and other aspects. If you can see in this data, the given variables are load, which has a unit of kilonewton, elongation, which has a unit of millimeter, and then there is strain, stress, slope. Strain doesn't have any unit because it's a dimensionless quantity. Stress, it is megapascal, and slope is the ratio between stress and strain. We look into it more as we go into the problem. Here, the right hand side of the table is the calculated data. So we will have to basically calculate this data by ourselves. The given data is load versus elongation. Now we have seen how to use this load versus elongation data for calculating material stiffness. This was previously. But now we will be seeing how to use the same data or similar data to calculate our stress strain and the respective Young's modulus. Here you can see we have loads and we have elongation. With load and elongation, we will have our strain and stress. And strain is nothing but the elongation of the actual length. So the actual length is usually given for a problem. And when it comes to the gauge length and also actual length, also termed as gauge length. When we take metal testing, gauge length is the word which we will be using. So when it comes to gauge length, we always have a fixed length. And now strain is nothing but the elongation divided by the initial length. So here whatever strain we see is the value which we gained from the ratio between the elongation and the actual length of the specimen used. Then we have to calculate our stress. Based on stress theory, force divided by the cross-sectional area is given as stress. So we always know our cross-section of the material, and we can use the load value that it is getting and then calculate the respective stress. Once we have our stress and strain, the acquired stress is divided by strain, from which our slope is obtained. Finally, this slope is our Young's modulus. By slope, here we have to plot all our stress and strain values against each other to get our Young's modulus. By plotting these values, we also find other materials like different stresses that include fracture stress, ultimate stress, yield stress, and the proportional stress and proportional limit. Although we have all these values, the highest value of the slope that we can get from the graph will be our Young's modulus for this problem. So after plotting, this is our data. We have plotted the stress strain data. So on the left hand side you can see the entire plot for all the data, and in the right hand side you can see that the plot is just for the elastic region. This kind of a plot will help us to closely monitor the various aspects that happen inside the elastic region easily. As you can see from this diagram, these two diagrams are proper examples for a totally plotted data and for a elastic region based plotted data. And if we can see in the table which is given, the diameter and gauge length is already given for the specimen used. From whatever we have plotted, we have taken the values for the limiting stress, yield stress, ultimate stress and fracture stress. And the values are for limiting stress, it's 55, yield stress it's 71, ultimate stress it's 126 and fracture stress is 112.8. To figure out the yield stress easily, if we can see in this plot that we have made inside the elastic range, when we extrapolate our line from the 70th mark of stress, we will get the yield stress as 71.3, which will be the closest to this area. We know that yield stress is the first point where the material is transitioning between plastic and elastic regions. So right now the transition is somewhere around here. But one thing which we have to note is that it is more than acceptable if you use the previous point as your limiting stress. If we go back in the slide, you can see that the fracture and the ultimate stress is given, and the highest stress here would be our ultimate stress. But other than this, a data which is not given in this table, which is the Young's modulus, can also be calculated using the given sheet data. In this sheet data, we already discussed that the Young's modulus is the highest value which we derive when we are finding the slope. And in this sheet, the highest value which we can get from the slope is 47,500. But there is one catch. This Young's modulus value can only be obtained from the first four values, because Young's modulus value always falls inside the proportionality limit. And by the given graph, we know that the yield stress happens at 71.3. So any slope value below this 71.3 would be our Young's modulus. Now that we have a better understanding of the stress strain plot, we can go ahead and solve a problem based on that. So the problem which we will be seeing here will be from the given data. Member AB is a rigid member. We have one more member which is CD, and this CD member is made of 2014 T6 aluminium, and the cross sectional area of CD will be 0.5. General given data can be seen as AD is equal to 3 feet, AB in total is 8 feet, and C is the midpoint, so AC is 4 feet. So we are asked to find the magnitude of force P, which is the load given here, and it is also given that due to this force P, the point B is displaced to 0.3 inches. Now let us solve the problem. So basically from the question we'll have to find the value of P, which is the load applied to deflect B to about 0.03 mm. There are few given values which we can take from the material data sheet. Those values are, first it's the Young's modulus of aluminium, and that would be E of Al. Its Young's modulus we know that is denoted as E, and E of Al is the Young's modulus of aluminium, and the value of Young's modulus will be 10.6 into 10 to the power 3 ksi. Next we can also get the value of the yield stress of aluminium, which is sigma y, and that is 60 ksi. Next we'll take the triangle ADC. The value of AD is 3 feet, and when we convert it into inches it's going to be 36, and when we add the deflection with it, it's going to be 36.03. DC will be L2 after elongation value, and AC will be 4 feet, which is 48 inches. Now to find the value of L2, we'll use trigonometry. L2 will be equal to root of 36.03 the whole square plus 48 the whole square. So therefore we'll get the value of L2, which is 60.09. Same way we'll take the triangle again, but this time it's before the elongation, and we are going to take the value of L1. And again AD is going to be equal to 36 and AC is equal to 48. So the value of L1 after trigonometry calculation is going to be 60. Now this is going to be 60.09 mm. Same way L1 is going to be 60 mm. From this, as for the elongation, it's going to be L2 minus L1. So elongation equals L2 minus L1, and we'll get 0.09 mm. Now that we got the value of elongation, the next thing we have to see is if the stress applied here, or the stress that the membrane or this beam is undergoing, it should fall inside the proportionality limit. So only if it falls inside the proportionality limit, we can continue this problem with the equilibrium equations. For that stress to fall inside the proportionality limit, it should be lesser than sigma y, which we just saw here. Sigma y is our yield stress of aluminium. It should be, the stress that this beam is undergoing should be lesser than sigma y. So we know that right now we are going to calculate the stress that this membrane CD is undergoing. Now for that, sigma CD will be equal to Young's modulus into epsilon. So we know that epsilon is equal to elongation divided by the original length. This is from the strain formula. So now, because we know the Young's modulus from the given values, we will substitute those values here, that is 10.6 into 10 to the power 3 into, we found the elongation previously, so we will substitute that value here, 0.09 divided by the original length, which is 60. Now after simplification, sigma CD is equal to 15.92 ksi, which is obviously lesser than sigma y, which is equal to 60 ksi. Now we know that the stress value falls well under the proportionality limit because 15.92 is lesser than 60. Now we got sigma CD. The next step for us is to calculate the load, which is P. So for that, first we need to create the free body diagram for our beam. As for the free body diagram, so we will take a rectangle. We know that we have a point A here and we have a load P here, and also this is a cantilever beam. Because this is a cantilever beam, we will be having one horizontal reaction and one vertical reaction. So the horizontal reaction is going to be AX and vertical reaction is going to be AY. As for these membranes, which is A, D and C, so we have a resultant force FCD that's acting here in this membrane, which is CD membrane, and using trigonometry, and we know that the value of AD is 3 and the value of AC is 4. So using trigonometry, it's going to be FCD into 3 by 5, and our horizontal reaction is going to be FCD into 4 by 5. Now from Hooke's law, which we already saw, sigma is equal to force by area. Therefore FCD is equal to sigma CD into area. The area is already given with the question, so that will be equal to 7.96. We've just substituted the value of sigma CD and A here. So for reference, I'll just write the values of these two variables into 0.5. By simplifying, we'll get the force as 7.96. So now, why did we draw the free body diagram here? To get our load value. So to get the load value, we are going to use the equilibrium equation. Summation of all the moments will be equal to 0. So we can also write it as the first reaction, which is 3 by 5 into FCD minus P into 96. Here 96 is the length of the beam, which is 8 feet, which is equal to 96 mm. Now with that, we also know the value of FCD. Therefore P into 96 will be equal to 7.96 into 3 by 5, and P will be equal to 7.96 into 3 by 5, and we get 96 here. So therefore the value of P will be equal to 2.39. Because we are dealing with inches here, our load is going to be 2.39 psi. In this section, we will also look at a different type of a proportional constant that is associated with shear stress or shear strain. Previously, we saw a proportional constant which is Young's modulus, and Young's modulus is a proportional constant for normal stress or strain. Now, before that, we look deep into Poisson's ratio. Simon Poisson in 1825 carried out the experiment for Poisson's ratio. He studied and established theories about lateral deflection of materials. He established that whenever a bar undergoes tension, lateral contractions are developed. So if you see in this example on the right side, when the body is elongating, its height is decreasing. So this was basically Poisson's effect. This is what Poisson realized in the year 1825. With this, he gave the Poisson's ratio or Poisson's effect. So basically, whenever there is a decrease or whenever there is a change in one aspect of a material's dimension, then there is a proportional change in the other aspect or a different dimension of the material. For example, if there is a change in the length of the material, for example, if there is a decrease in the length of the material, then he observed a increase in the breadth of the material. We can see that a little more in detail here. So for example, when we take the strain in the longitudinal direction, if there was a positive change in the longitudinal strain, then there was a negative change in the lateral strain. So for example, if we take this tube as a specimen, when an axial load acts on this tube, it increases the length of the tube, which in turn decreases the diameter of the tube. So basically there is a decrease in the cross-sectional area of the tube. So we can say that when there is a positive strain that is happening on the tube, we can observe a negative lateral strain in the same tube. At the same time, similarly, when there is a negative strain happening on the tube, or when the tube is undergoing a negative strain, we can observe a positive lateral strain. So basically, when the axial load is acting inwards, we can observe that the length of the tube is decreasing, but a bulge in the tube is happening, and because of this bulge there is a increase in the diameter of the tube. But one point we should note here is that although there are deformations in the lateral directions, no load has been applied in those directions. So the load which was applied in this tube was only in the axial direction. Still, we could observe the changes in the lateral directions too. There is one more point we need to keep in mind, which is the changes are always in the lateral and longitudinal directions and not in the volume of the same tube. So next we will see the derivation of Poisson's ratio. Considering a bar under uniaxial tension, Poisson observed and reported that under uniaxial loading, strains in y and z directions are proportional to the strain in x direction. So basically, the strain in the x direction was proportional to the strains in the y or z direction. From that, we can say that epsilon y was directly proportional to epsilon x, and the same way epsilon z was also directly proportional to epsilon x. But because there is a proportionality happening here, the proportionality constant was given as the Poisson's number, which is nu. We call this as nu. The proportionality constant for Poisson's ratio is nu. So therefore epsilon y was equal to minus nu epsilon x, and the same way epsilon z was equal to minus nu epsilon x. Now let us see an example for Poisson's ratio. We will consider this rectangular bar for the example. Now considering a rectangular bar, compute the expressions for axial stiffness and axial lateral deflections. So usually we calculate normal stresses and strains with the formula of sigma x, which is equal to load by area. Here load by area is P by BD. Area is equal to breadth into depth. And again epsilon x, which is the strain, will be equal to sigma x by E, wherein sigma x is our stress and E is our Young's modulus, which is the proportionality constant. So we can give it as, by substituting the value of stress in the strain equation, we get P by E into B into D. So therefore the extension in the axial direction, which is the x direction, we can see here in the diagram given in the right side, the stress given here is in the axial direction, which is x direction. So the extension is given as u, which is equal to epsilon into the original length. In the previous slides, we came across a formula for strain, which was elongation divided by the original length. Here original length is capital L and u is our elongation. So therefore we can also say that u is equal to PL divided by EBD if we substitute the previous equation which we got for epsilon x. Now by reordering this equation, we can say that stiffness is equal to EBD by L. Here we already know that stiffness is equal to the applied load by whatever elongation we got. From the previous slide, by reordering we can also say that stiffness is equal to EBD by L. From this equation, we can conclude that for every increase in cross-sectional area and for every increase in Young's modulus, the stiffness value also will increase, because K is directly proportional to the cross-sectional area and directly proportional to the Young's modulus. At the same time, stiffness is indirectly proportional to length. So for any decrease in the length or for any increase in the length, we can observe increase in stiffness or decrease in stiffness respectively. As for the lateral contractions, in the previous slides we already saw the equation for Poisson's ratio, which is axial strain divided by lateral strain will give us the Poisson's number, which is nu. So for the V direction or for the V axis, V will be equal to epsilon y into d, which is the lateral contraction. But we can substitute the value of epsilon y which we get from the Poisson's ratio. So by substituting that, we get minus nu epsilon x d as our contraction on the V side. So by simplifying the other equations in this final equation, we get minus nu into the load applied divided by the Young's modulus into breadth. Similarly for W, we get the same equation, but because we are dealing with the W side, we get d instead of b here. Now let us go through an example to get a better understanding of how we deal with Poisson's ratio. 2014 T6 aluminium bar is loaded as shown. We'll have to determine the normal strain in the x, y and z directions. So from the given question, we are asked to determine the normal strain in the y, x and z directions. Here y is our axial direction. Now there are few given values that are given in the problem only. We'll first consider those values. The first value is the E equals 10.6 into 10 to the power 3 ksi. Now this is the Young's modulus. Next it's sigma y is equal to 60 ksi. This is the yield stress. Next we are also given the Poisson's ratio, which is nu equal to 0.35. Now before going into the solution, we will need to find the cross-sectional area. So if we take the rectangle, the breadth is given as 0.5 and the length is given as 0.75. Therefore, the cross-sectional area for x will be equal to 0.5 into 0.75, which is equal to 0.375. Now we will figure out the stress that is being applied. Sigma axial, which is the axial stress, is equal to F divided by A, which is force by area. Now we can also term sigma axial as sigma y, because the axial direction is given as y here. So sigma y is equal to F is 15 kip, which is 15 divided by, we got A here as 0.375, so 0.375. Therefore sigma y is equal to 40 ksi. Now we already have the yield stress, which is 60 ksi here, and it's evident that sigma y here is lesser than sigma y of aluminium as a whole. So basically 40 ksi is lesser than 60 ksi. Okay, now that we got the stress, next we'll calculate the different strains. So we'll have to calculate all the normal strains in x, y and z directions. We'll first calculate the strain in the y direction, which is straightforward. We'll use the strain formula, which is sigma by E, and by that it will be 40 divided by 10.6 into 10 to the power 3. Therefore sigma y will be equal to 0.003774. So we got the strain in the y direction. Now we need to calculate the strain in the other two directions, which are x and z. Here we were terming it as sigma, but this is actually epsilon. Now epsilon x is equal to epsilon z, which is equal to minus nu epsilon y. So by that it's going to be 0.35, which is the value of nu, into epsilon y. We already got the value for epsilon y here, which is 0.003774. Now by simplifying this, epsilon x is equal to epsilon z, which is equal to minus 0.00132. This will be the value for our strain in x and z directions. We were supposed to find only the normal strain, but we'll extend this problem a little bit by finding the elongation also. Now for elongation, we know that epsilon is equal to elongation divided by the original length. We know the original length already. As for the x direction, the original length is 0.75, and for the z direction, L is equal to 0.5. Again epsilon is equal to del z by L, and here it's going to be del x by L. Now we know the value of L and we know the value of epsilon. So with that, del x is equal to epsilon x into 0.75, which is equal to minus 0.00099 inch. The same way, del z is equal to epsilon z into 0.5, which is equal to minus 0.0006 inch. Now one thing we'll have to understand here is, although the strain values for the x and z directions were same, it's not the same with the elongations. The elongation values are different for x and z. With that, we come to the end of this session. So this week was all about learning about the mechanical behavior of materials. We saw mechanical properties of materials like stress, strain, Poisson's ratio, etc. We also stressed on the term strength, and we saw its importance with materials. We came across types of simple stresses and strains that can be applied on materials. We also saw a few stress strain diagrams wherein we came across the relationship between load and deformation, which was basically stiffness. Then we came across a very important material property, which was Young's modulus, and we defined its relationship between stress and strain. Finally, we concluded the session with an overview on Poisson's ratio and its effects on shear stress and strain with a problem. With that, we'll see you on a different video with different concepts. Till then, take care. Thank you. Welcome to the second week of the course Strength of Materials, and in this week we'll be learning about multi-axial systems and stress transformations. So in the previous week, we saw the variation between elastic and inelastic properties of a material. We went ahead plotting and understanding the features that are involved in a stress diagram. We also saw some of the aspects of the term strength. Also, came across aspects of strains and their relationship with stress and structural behavior during loading. We looked into the relationship between shear stress and normal stress, and we finally concluded that session with the Poisson's ratio after solving few numericals. So now that we have a better understanding of what stress and strain is, and also we have a better understanding of what are various stresses and strains. So for this week, the table of contents will be as follows. First, we'll start with plane stress transformation, and then we'll be solving few general equations for plane stress transformations, and then we'll also be going through few problems. Then we'll go on solving principal stresses and maximum in-plane shear stress. Next, we'll be seeing about Mohr circle for principal stress and end this session with absolute maximum shear stress. As for the learning objectives, we will be discussing about stress transformations and its applications. Then we'll see some methods to solve problems based on stress transformation efficiently. Then we'll also come across differences between normal stresses and principal stresses. We'll learn the differences between normal stress and principal stress. We'll go through techniques for plotting Mohr circle, and we'll also go through some stress transformations for advanced applications. Now let us directly go into plane stress transformation. In statics, stresses acting on a body changes with the rotation of the body due to applied forces. So here, stress is considered positive if it's in a positive phase or posnate coordinate direction on the elements. In the same way, it is considered negative if it's in a negative coordinate direction on the elements. So now, what are three-dimensional stresses? In the right side image, if you take this cube is called as the three-dimensional stress element. And the same way, this square which you can see here is called as the two-dimensional stress element. Now this square we have derived from the cube which we have on the left hand side. Now we always know that there are three types of stresses that is acting on this 2D element. Two will be normal stress and one is the shear stress. Here the normal stress or the axial stress, you can call it sigma y and sigma x, and the shear stress that is acting is tau xy. Now, as for the variables, you can only see the notation as y or x here, and because it's shear stress, you can see xy. At the same time, if you see in this 3D structure or the cube which is given, there are different types of stresses that we can see, which is sigma x, sigma y, and sigma z2. So, sigma z is the third plane of stress. And when we see the third plane, we can also come across tau zx and tau zy. Now, if we take a surgical glove, so in the right side, you can see there is a white color diagram inside which there are two boxes drawn. One is a square box and the other is a rhombus. Now, imagine this white color boundary is a surgical glove, and this surgical glove is stretched, and the stretch is happening as it's given in the below diagram. You can see that the square box is undergoing only a change in its dimension, which is length and breadth. So this is basically undergoing a normal stress. At the same time, if you can see the rhombus, it is undergoing a change in all of its angles. So this means that it's undergoing a shear stress. Now, going through all this, the two things which we have to keep in our mind. The first one is the sign convention, which we saw already, which is if it's in a positive coordinate direction on the element's positive phase, it is a positive stress. And it's called a negative stress when it is acting on a negative coordinate direction on the element's negative phase. Now, one more thing is we have to consider the state of stress at a particular angle inside an element at a particular point. Now, if we have to consider a state of stress at a particular angle inside the element at a particular point, which is making a certain angle with the normal or with the x direction. So, if you can see in this diagram, this square is making a particular angle theta with this straight square. So, at that particular point, if we have to calculate the state of stress, we have two methods to calculate it. One is using equation method and the other is using the Mohr circle. Now we'll be seeing both these methods eventually, and first we'll be going through the equation method. So general equations for plane stress transformation is what we'll be seeing now. Now taking a square element or a 2D element, like how we saw back in the slide, we know that sigma x is going to be our normal stress. Same way, sigma y is also going to be the same, but sigma x is going to be in the x direction and sigma y is going to be in the y direction. Same way, as for the shear stress, it's going to be tau xy, which is shear stress. Now tau xy is in our xy direction, and for a 2D plane or for a 2D element, we'll only get xy because we only have two directions, which is x and y. And also we should keep in mind that if it's a tensile force, it's going to be positive, and if it's going to be a compressive force, then it's negative. This is our sign convention. Now, if we take the square which is here, this is the orientation which we saw first for our sigma x, sigma y and tau xy. But imagining there is a change in the orientation. So now, after the change in orientation, we are going to call the stresses and tau with a dash, which is sigma x dash, sigma y dash and tau x dash y dash. Now, these are all new stresses. Now that we have taken these stresses from a new orientation, it also means that this new orientation, I'll write it as new orientation, is formed due to an angle theta, right? So that angle is given here as theta. Now, I've taken this triangle, which is basically the triangle that is formed due to the original element and the new element which was formed due to the orientation angle theta. Now for the equations, okay, we know that stress is equal to force by area, and from free body diagrams and from equilibrium equations, we know that the summation of forces should be equal to 0. This is what is given in the equilibrium equation. Also, if we take a free body diagram as in a triangle, now from trigonometry we know that if the hypotenuse is f, then the corresponding horizontal is sin theta and corresponding vertical is cos theta. So now with that we'll start creating our equations. Now we know the formula for stress, which is sigma equal to f by a. This can also be written as f equal to sigma into a. Now here we have f1. So for all those formulas, f1 will be equal to sigma y dA sin theta. f2 will be equal to tau xy dA sin theta. f3 here will be equal to, f3 is again axial stress, but it's in the x direction. So sigma x dA cos theta, and f4 will be equal to tau xy dA cos theta. Now the two reactions which we need to find are fx dash and fx dash y dash. So these are the equations which we get after we tilt the element of an angle theta. So we know that summation of all the forces is equal to 0. By substituting this formula here, f of x dash will be equal to f1 sin theta, which is here, and plus F2 cos theta plus F3 cos theta plus F4 cos theta. Okay, we'll move to a new page. Now we have all the needed equations here. With that, we'll go ahead. So f x dash is equal to sigma y dA sine square theta plus tau xy sine theta cos theta dA plus sigma x dA cos square theta plus tau xy sine theta cos theta dA. So previously with the free body diagram which we made, we can also get the equation for f x dash, which is sigma x dash dA. Now substituting f x dash equation here, we'll get sigma x dash dA. After substituting, we can see that dA is common for f x dash and the right side equation too. So we can easily cancel out dA in every available equation here. So instead we can write the new equation, which is sigma x dash is equal to sigma y sine square theta plus tau xy sine theta cos theta plus sigma x cos square theta plus tau xy sine theta cos theta. Now that we got this equation, the next thing which we'll have to see is we have some trigonometric equations which we can substitute here. The first one will be cos square theta, which is equal to 1 plus cos 2 theta divided by 2. And the same way we also have sine square theta, which is equal to 1 minus cos 2 theta by 2. There is a third equation which we'll have to take care, which is 2 sine theta cos theta, which is equal to sine 2 theta. Now substituting all these equations in the above formula, sigma x dash will be equal to 1 plus cos 2 theta by 2 into sigma x plus sigma y into 1 minus cos 2 theta by 2 plus tau xy sine 2 theta. We can further simplify this equation to sigma x dash equals sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sine 2 theta. Now we've got the equation for sigma x dash. Now this is for the x direction. The next one we'll be looking at is the y direction. Summation of f x dash y dash is equal to 0. Now due to sign convention and because it's in the y direction, we have some changes in the parent equation, which is f of x dash y dash minus f1 cos theta plus f2 sin theta minus f4 cos theta plus F3 sine theta. Now we have this difference in the signs because if we take it in the y direction, we can see that F1 is going downwards, so it's going to be negative, but F2 is going the other direction, so it's going to be positive. The same way it's for F4 and F3. Also, like how we took the equation for Fx dash, we'll take the equation for Fx dash y dash, which is equal to tau x dash y dash dA. Now substituting these equations here, tau x dash y dash dA minus sigma y dA cos theta sin theta plus tau xy dA sin square theta minus tau xy dA into cos square theta plus sigma y dA into cos theta sin theta. Now we can simplify this formula to tau xy dash minus sigma y cos theta sin theta plus tau xy into cos square theta minus sin square theta plus tau x into cos theta sin theta. With the help of trigonometric formulas, we'll simplify more in this equation. By trigonometry, you know that cos square theta minus sin square theta is equal to cos 2 theta. Also, sin theta cos theta is equal to sin 2 theta by 2. By substituting these trigonometric formulas in the given formula, we get tau x dash y dash plus sigma x minus sigma y into sin 2 theta by 2 minus tau xy into cos 2 theta, which is equal to 0. Now all these equations are equal to 0 because that is how we define it with the equilibrium equation, which is sum of all forces. So because we have equated all the left hand side to 0, now we can make this left hand and right hand side equation. Tau x dash y dash is equal to tau xy cos 2 theta minus sigma x minus sigma y sin 2 theta by 2. Now this will be our equation for shear stress. Previously we saw the equation for normal stress. Now this will be the equation for shear stress. Now with that we can go into some numericals of the same equation. Now after solving all those equations, we get to this point where we get the equations sigma x dash, sigma y dash and tau x dash y dash. When we take the normal stresses, the only difference between them is that the direction for the first normal stress is in the x direction and the second one is in the y direction. So we only get a directional change, which is for sigma x dash there is a positive note here, and for sigma y dash we have a negative note here or negative symbol here. Now we'll just go through few steps for any plane stress transformation related analysis. First one is to sketch the desired surface. If we are given a problem, we'll need to first sketch the desired surface and then mark all the normal stress and shear stress. With that, we'll have to determine the angle from the actual positive x-axis to the normal. Now this angle is the angle which we mark after we get the orientation of the new plane. After marking this angle, we then draw the rest of the new square and label the positive y dash axis, which is 90 degree clockwise from the positive x dash axis. Then later, using the sigma x dash, sigma y dash and tau x dash y dash equations which we derived in the earlier slides, we'll try to find the values for all these variables. One main thing which we have to keep in our mind is we'll have to keep applying the proper sign conventions for us to get correct dimensions or correct values of the stresses. So here we are given a very simple problem related to the equations which we just derived. So the statement is, for each state of stress given, find out the normal and shearing stresses exerted on the surface indicated. Now we can see the actual square element here, which has 40 MPa and 80 MPa as its sigma x and sigma y respectively. So the new square which is oriented to 55 degree is also given. With that, we are going to find the values for the normal and shearing stresses. So from the question, what we have is a square element with sigma y and sigma x as 80 and 40 MPa. Now we can term this as sigma y and this as sigma x. As for the sign convention, we can see that this is a compressive stress, or this stress is inward. If the stress is inward, then it's negative, and if the stress is outward, it's positive. The same way, if we take shear stress, if the shear stress is in this direction, it's positive, and if it's in the opposite direction, it's negative. So from the question, sigma x will be equal to minus 40 MPa, and this is because of inward direction, and sigma y will be equal to 80 MPa. But because we didn't get any information regarding tau xy, we'll just keep tau xy as 0. Before going to the question, we'll need to figure out a very important value, which is theta value. Now from the question and from the diagram, we can see that theta is 55. Theta is 55 degree. Now the stress is acting inwards like this. So this line is going to be parallel to this line. And if we extend this line with alternate angles, this angle is going to be 55 degree. Now, if we draw a straight line here, then the summation of these two angles is going to be 90 degree. So this angle is going to be 35 degree. Again, the summation of this angle here is 90 degree. And we'll need to find out, or we'll need to figure out the value of this angle, which is theta, which is the needed theta value. Now again, we know that the angle formed between these two lines will sum up to 90 degree. So because of that, this angle will be 55 degree, and again theta will be equal to 35 degree. So therefore, we get the value of theta as theta equal to 35 degree. Now we'll have to figure out the new stresses. So first we'll go ahead and directly write the formula for sigma x dash, which is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy into sine 2 theta. Now because we have not given tau xy, or tau xy is basically 0, we can just equate this formula to 0. And with the rest of the formula, we'll have minus 40 plus 80 by 2 plus minus 40 minus 80 by 2 into cos 70 degree. Now by simplifying, we'll get sigma x dash is equal to, will be minus 0.521 megapascal. Now the value of sigma y dash will be equal to 40.52 megapascal. As for tau x dash y dash, we know the formula, which is sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. Now again we can equate tau formula to 0 because we know that tau xy is equal to 0. So with that, by simplification, we get tau x dash y dash, which will be equal to minus 56.4 megapascal. Now, one important thing which we'll have to note here is, even though tau xy is given as 0 here, tau x dash y dash has a value of 56.4 megapascal. And this says that the stress applied even without shear stress is going to create another shear stress when there is a different orientation. So by drawing the new square, which has an orientation of 35 degree, we can say that a sigma x dash is inwards, and it has a value of minus 0.521 megapascal, and sigma y dash is outwards because we know that the value of sigma y dash is a positive value, so it's 40.52 megapascal. And again, tau x dash y dash is and that's given as minus 56.4 megapascal. Concept called principal stresses and maximum in-plane shear stress. First, we look at principal stress. So what does principal in-plane normal stress mean? The maximum and minimum normal stress in a plane at a particular point is called principal in-plane normal stress. One thing which we have to keep in mind, that when we talk about principal in-plane normal stress, the value of shear stress acting in the same plane is taken as 0. So we only talk about normal stresses which can be maximum or minimum in a given plane at a particular point. Now to derive that, let us move on to the whiteboard. In our high school, we would have come across something called critical points in our calculus classes. We would have come across something called minimum and maximum points, in which if I draw a quadrant and if I have d of f by d of x equal to 0, then if we have a graph like this, the truss and lowest point are given as 0, which is the maximum and minimum point. Here we can say that this is the maximum and minimum point. So now, from the previous derivations, we know that sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos 2 theta plus tau xy sin 2 theta. Now to get our maximum and minimum values, we'll differentiate both left hand side and the right hand side with d theta. So therefore, d sigma x dash divided by d theta is equal to d by d theta of sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. So we know that the value here is 0. So 0 minus 2 into sigma x minus sigma y by 2 into sin 2 theta plus 2 tau xy cos 2 theta. Now this is our value after differentiating. Because we have equated this equation to 0, we can take in left hand side and right hand side consideration, and we'll get 2 tau xy cos 2 theta equals 2 into sigma x minus sigma y by 2 into sin 2 theta. Now here, if we again reorder the equation, we'll get tan 2 theta. We get tan 2 theta here because if cos and sin are reordered, and we know that by trigonometry tan is equal to sin by cos. So therefore tan 2 theta is equal to tau xy by sigma x minus sigma y divided by 2. Now because we are working with normal stresses wherein we have to consider both tau and sigma, and in this formula we can see that we have both the variables tau and sigma. When we plot this tan 2 theta value in a graph of tau and sigma, we'll get something like this. So if I take a graph of 4 quadrants or coordinate of 4 quadrants, wherein the vertical axis is tau and horizontal axis is sigma, the plot is going to be a triangle wherein the horizontal value is going to be sigma x minus sigma y by 2 and the vertical value is going to be tau xy. And when we plot it for 2 theta, we know that tan is equal to opposite by adjacent. And at the same time, from the Pythagoras theorem, the hypotenuse can be written as root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square. Now going back to our stress equation where sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. Now going back to this formula of ours, now that we know what values we have in the hypotenuse, opposite and adjacent side of 2 theta, we can substitute values for cos 2 theta and sin 2 theta because we know that cos theta is equal to adjacent by hypotenuse and sin theta is equal to opposite by hypotenuse. Now after substituting and simplifying, we get sigma x is equal to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 the whole square plus tau xy square. Now because we have values in both the quadrants and we know that the in-plane normal stress is both maximum and minimum, we have one more triangle to take care of with the same 2 theta. And now here our tau value is going to be minus tau xy, and same way our sigma value is going to be minus sigma x minus sigma y divided by 2. Because we have two values to consider, but only change that is happening here is in the direction or you can also call it as negative and positive signs. So the only difference that comes here is in the sign convention. We can generalize the formula as sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus or minus root sigma x minus sigma y by 2 the whole square plus tau square x y. We can see here that after we substitute the values of cos theta and sin theta in the sigma x value, and we know that there will be two values given because of sign convention, we'll get this equation which we finally arrived upon. So some of the observations which we have to take care is that sigma p1 and sigma p2 are 90 degrees apart from each other. And there are no shear stresses at the point of principal stresses. We already saw that principal stress is only the maximum and minimum point of normal stress that is happening in the principal plane. Also, we should take care and we must test the value of theta p to ensure the value of theta p1. Now we'll move on to maximum in-plane shear stress. So as for maximum in-plane shear stress, it is exactly similar to what we saw with in-plane normal stress, but this time we are going to use the third and fourth quadrants. So in the first normal shear stress, we were using the first and the third quadrant. This time we'll be using the second and fourth quadrant. And by doing the same calculations, just that we will change our parent equation for the shear stress equation, which is tau x dash y dash. We'll arrive at a tau maximum where it's maximum in plane, and that will be root over sigma x minus sigma y by 2 the whole square plus tau xy the whole square. And here we should also note that we'll get an average value which is sigma average, that will be equal to sigma x plus sigma y by 2. We get average value when we don't have shear stress with us. And the observations which we have to note here is that theta p and theta s are 45 degrees apart from each other, and at the point of maximum in-plane shear stress, there is a average in-plane normal stress. So next, we'll go ahead and solve a problem. The statement given here is for each state of stress given, we'll have to determine principal stresses and their orientation, and we should also figure out the maximum value of in-plane shear stress and average normal stress and their orientation. Now, this is going to be a straightforward problem. Let us again jump into the whiteboard. So, from the question statement, we need to figure out principal stresses and their orientation, and then we'll have to find the maximum value of in-plane shear stress and average normal stress and their orientation. First, let us note down the given values. So, from the diagram, sigma x is given as 2 ksi, and then sigma y is given as 10 ksi, and tau xy is equal to minus 3 ksi. So first let us write the equation for principal stress, which is sigma p, that is equal to sigma x plus sigma y divided by 2 plus root of sigma x minus sigma y the whole square plus tau xy the whole square. With that, if we substitute the given values, which is 2 plus 10 by 2 plus 2 minus 10 by 2 the whole square plus minus 3 the whole square. So we'll get the value of sigma p as 11 ksi. Now when we do the same thing, so this is for sigma p1, we know that this formula is plus or minus formula. So we first did it for sigma p1, and let us consider the positive sign convention here. In the same way, for sigma p2, giving a negative sign convention, we'll get the value 1 ksi. We got both P1 and P2, our next step is to determine the angle of orientation. Now, for that, we know the formula T tan 2 theta P, which is equal to tau xy divided by sigma x minus sigma y by 2. By substituting the given values here, we get 2 theta P as 36.9. So we came over few observations which was given for principal stress or for plane normal stress. The 2 theta value ranges inside plus or minus 180. So basically 2 theta P1 to 2 theta P2 falls under plus or minus 180. So therefore, if we get 2 theta P equal to 36.9, then we got one value of 2 theta P as 36.9. Then if it falls inside 180, then it should be 2 theta P, which is equal to minus 143.1. So what we have done is, we have subtracted the first value from 180. Again, from the same observations, we also got that theta 1 to theta 2 values fall under 90 degree. Again, if 2 theta P is equal to 36.9, then theta P is equal to 18.45. Therefore, one more theta P value should be 90 minus 18.45, and it is minus 71.55. Now here, if you can see, I have given one positive value for 2 theta P and one negative value for 2 theta P. In the same way, I have given one positive value for theta P and one negative value for another theta P. This is because we know that the normal stress should be falling as one negative and one positive value, because we have a quadrant in which this is positive and this is negative. Now with that, to figure out sigma P1 and P2, we'll again substitute the theta value in the normal stress equation that we saw earlier. So the stress equation which we saw earlier was sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So this is tau. So after substituting whatever values we got, and let us take 18.45 as our first value to substitute here, and we'll get sigma x dash as 1 ksi. Now sigma x dash is equal to sigma P2, right? So sigma x dash is equal to sigma P2. Therefore, 18.45 is theta P2. And the value of theta P1 will be equal to minus 71.55. Now, as for the orientation, so if we take a straight line, then the angle between this is, for example, minus 71.55. Then the oriented plane for minus 71.55 degree angle is going to be this, wherein sigma P1 is equal to 11 ksi and sigma P2 is equal to 1 ksi. Now both of these sigma values are positive values, and that means that the stress is also outwards. And if these are negative values, we are going to draw stresses which are inwards. So our next statement is to find out the maximum value of in-plane stress and average normal stress and their orientation. So we'll take the next slide or the next board. As for the in-plane shear stress, As for the in-plane shear stress, the formula for in-plane shear stress is given as tau in plane is equal to plus or minus root over sigma x minus sigma y by 2 the whole square plus tau xy the whole square. We already know the given values, and if we substitute all these values inside, we get a value of plus or minus 5. Our next plan of action would be to find out the theta value, and that can be found out using tan 2 theta formula for shear stress, and that will be tan 2 theta is equal to minus sigma x minus sigma y by 2 divided by tau xy. After substituting, we'll get tan 2 theta as 4 by minus 3. Now 2 theta will be equal to minus 53.13 and theta will be equal to minus 26.6. Now we got one of the theta values. We also got the value for in-plane shear stress. Next, we'll figure out the average stress, which is sigma average. That will be equal to sigma x plus sigma y divided by 2. And after substituting, we'll get 6 ksi. So now to figure out the shear stress, if it's positive or negative, we'll substitute the theta value in the original formula. The original formula for tau x bar y bar is equal to, or tau x dash y dash is equal to minus sigma x minus sigma y divided by 2 sin 2 theta plus tau xy cos 2 theta. Tau x dash y dash is equal to minus of 2 minus 10 divided by 2 into minus sin 53.13 plus minus 3 into minus cos 53.13, and that will be equal to minus 3.19 plus 1.8, which is equal to minus 1.39 ksi. As for the orientation diagram, we can say that our normal stress is a positive value which we got from the sigma average calculation, and because it's a positive value, the arrows can be drawn outwards, and that is going to be 6 ksi. Our shear stress is a negative value, due to which our shear diagram or shear arrows can be drawn clockwise, which can be given as minus 1.39. So previously we used different equations for sigma x and sigma y. We also used equations for tau xy. With that, we derived equations for sigma 1, sigma 2, which are the maximum and minimum principal stresses, and also for maximum in-plane shear stress, which was tau max in plane. Now we'll use the Mohr circle instead of those equations to get the values for these variables. So what is a Mohr circle? It's just a tool that maps or represents all possible stress transformations in a circle. So like we discussed, we'll get values for sigma 1, sigma 2, which are the maximum and minimum in-plane normal stress, the tau max in plane, which is maximum in-plane shear stress, and then values for theta p and theta s, which are the angles of orientation in the principal normal stress and the shear stress. Now first we'll learn about setting up the Mohr circle. Basically first we'll draw horizontal and vertical axis, wherein the horizontal will be for normal stress and the vertical will be shear stress. And one thing which we'll have to keep in mind is that in the vertical axis, the downwards quadrant will be positive for shear stress. Later we'll have to plot values for sigma and tau, and these values will be given with the problem. And then for the center or origin of the Mohr circle, we'll have to calculate the average stress. Calculating average stress in the x and y directions will give us the center of the Mohr circle. With that center and the available points, we'll draw the Mohr circle. And then the angle inside the Mohr circle will be represented by 2 theta because we'll have a quadrant of 180 degree. And after determining the radius of the Mohr circle using geometry, using trigonometric ratios, or using Pythagoras theorem, we'll calculate the principal stresses and their respective angles. Not only that, we'll also calculate maximum shear stress and the angle it makes with the normal. Now we'll go ahead with this problem statement. So for the state of stress given, determine the following using Mohr circle, which is principal in-plane stresses, maximum value of in-plane shear stress and average normal stress. And we should also figure out the orientations of each of the above. Now we'll jump into the whiteboard. So what we see in front of us is the Mohr circle. We have a graph in which we have plotted the Mohr circle. Now we'll look how we plotted this circle. Before that, we'll address the scale value. So scale value for this graph. So scale is equal to 1 cell is equal to 2 units. This means that this 1 cell will be considered as 2 units. Okay, with that we'll go into the graph. So from the setting up of Mohr circle, we understood that the downward axis, the downward vertical axis will be the positive shear stress, and this can be called as the negative shear stress. The same way the right side will be called as the positive normal stress and the left side can be called as the negative normal stress. Now before going into the circle, we'll need to jot down all our given values. Sigma x here will be equal to 18 ksi. It's 18 ksi because the stress here is tensile stress and it's going outwards. So it's going to be plus 18 ksi. Next, sigma y will be equal to minus 12 ksi and tau xy will be equal to 8 ksi. Again, here the shear stress value is counterclockwise, so therefore it's going to be positive. Now we have the sigma and tau axis. Next, we'll have to figure out the first point. Our first point, which is going to be sigma x comma tau xy. So for that, we have 18 comma 8 as our first point. Now keeping this point as our origin point, I'll mark this point as our origin point, and our origin point is going to be 0 comma 0. When we take the scale, we get 18.8 here. So this is going to be our first point. So to figure out the center point, we'll have to calculate the average stress, which is sigma average. That will be equal to sigma x plus sigma y divided by 2. And from the given values, we know that 18 plus minus 12 by 2 is equal to 3 ksi. Now this point is going to be our center point, which is 3 comma 0. Now this is going to be our average stress, which is 3. Now we'll call average stress as C, and name this point as C. Our next step is to figure out the radius of this circle. So this is going to be our radius. So to figure out the radius, what we'll do is, okay, first we'll give these points as A and B. So to figure out the radius, we are going to use the Pythagoras theorem. So this line, which is the sigma line, is going to be CA. So we know that CA equals 2 plus 2, 4 plus 2, 6 plus 2, 8, 10, 12, 14, and then there is one unit here which is 15. So CA is going to be 15 and AB the same way is going to be 8. Therefore, our radius, which is R is equal to root of 15 square plus 8 square. Therefore, R is equal to 17. Now, R value is the value of tau xy or the value of maximum in plane shear stress or tau MIP. So, I am going to give tau MIP as plus 17 KSI. So, with that, sigma P1 is equal to C plus R. So, C plus R is C plus the radius. So, for us, this value will be C, and C plus R is equal to 3 plus 17, which is equal to 20 KSI. And sigma P2 is equal to C minus R. This region is C minus R, wherein we know that this small region is C and this whole line is our radius. So we'll just call this as DE. So DE is going to be R C minus R. 3 minus 17. And that is equal to minus 14 KSI. So now that we've got values for sigma 1, which is equal to 20 KSI, and sigma 2, which is equal to minus 14 KSI, and we know the values of these lines CA, AB, and the radius of the circle, which is 15, 8, and 17. Our next step is to figure out the orientation angle, which is theta P and theta S. So theta P is the orientation angle when it comes to the normal stress or the principal stress, and theta S is the orientation angle when it comes to maximum in plane shear stress. So for theta P, we have the equation tan 2 theta P, which is equal to opposite by adjacent. So it's going to be 8 by 15, and 2 theta P is equal to tan inverse of 8 by 15, and theta P is equal to 14 degree, or from this equation only 2 theta P is equal to 28.1 degree. The same way, from equations we know that the value of 2 theta S is equal to 90 minus 2 theta P1. So this is from geometry. So we have taken this from these angles wherein the summation of this angle is going to be 90 degree, and 90 minus 2 theta P will get 2 theta S. So we know the value of 2 theta P, which is 28.1. So 2 theta S is going to be 61.9 degree, and theta S is going to be 31 degree. So here we've got theta P as positive and our shear stress is going to be a negative orientation, which is minus 31 degree. So with that, we have found out values of theta 1, theta 2. In the previous board, we also figured out the value of tau MIP, which was the radius of the circle, which is 17 KSI. And then later we also figured out the values for theta P, which is 14 degree, and theta S, which is minus 31 degree. With that, we'll move on to the next concept, which is absolute maximum shear stress. Now, the strength of any ductile material depends on that material's ability in resisting shear stresses, making this a very essential part for us to calculate the absolute maximum shear stress in that material system which is under loading. Now, we can do this using Mohr's circle, and we'll be focusing more on the volume elements in order to do this. So what we see on the screen is a 3D element. So this 3D element has 3 directions, X, Y, and Z. And then we have made them into 3 parts of 2D elements. The first one is XY plane, the second one is the ZX plane, and the third one is the YZ plane. So now we'll move on to the whiteboard to see on few important terminologies that we'll be using for calculating the principal stresses on volume elements. Now, in the first element, which is the XY element, we know that X has a stress of 450 psi. So we'll give 450 psi here. And in the same way, the next is going to be our Y element, for which the stress is 250 psi. So if we keep plotting these, again for the X element, the stress is 450, and for Z, it's going to be 150, which is inwards. We'll have to keep this in mind. The Z direction stress is inwards. So 150, and for Y, it's 250. So here, we can say that our sigma maximum, which is the maximum stress, is 450 psi, and our sigma minimum is the Z direction stress, which is 150, and we know that it's an inward stress, so it's negative 150 psi, and the intermediate stress is, for this problem, it's going to be 250 psi. So basically, our maximum stress is sigma X, minimum stress is sigma Z, and intermediate stress is sigma Y. Also, to find out the maximum shear stress or maximum absolute shear stress, we'll use the formula sigma X or sigma max minus sigma minimum divided by 2, where this equation, which is sigma max minus sigma minimum, will be the diameter of the circle which we plot in the Mohr's diagram. Now, as for the Mohr circle, first we'll give our coordinates, which is the tau coordinate and the sigma coordinate. So this will be sigma and this will be tau. And as for the circles, we'll have to first plot the points. The first point will be our maximum point, which is sigma max, and that will be 450. And next we'll plot the minimum point, the sigma minimum, and that will be minus 150. And as for the circle, this is our bigger circle. Now, the circle which we have plotted here is for the ZX plane. So, the ZX plane will have the biggest circle where we have 150 and 450, which is minus 150 and 450 as our stress values. So, let us call this the ZX circle. The next point which we'll have to take care is the intermediate point, which is 250. So we'll plot that point somewhere here. This will be our intermediate point. And as for the intermediate point, this will be the smaller circle, and this will be the intermediate circle. Now, this circle is governed by minus 150 and 250. So therefore, this circle is the Mohr circle given for the plane YZ. And the same way, this circle is governed by the points 250 and 450. Therefore, this circle is governed by the XY plane. Now, as for the plot of tau max ABS, it's going to be the diameter divided by 2, which is basically the radius of the circle. And here, for us, sigma max is going to be 450 and sigma minimum is going to be 150. Therefore, our value for sigma max minus sigma minimum divided by 2 is going to be 450 minus of 150 divided by 2, which is equal to 300 psi. Now, we can mark 300 somewhere here, and finally, this point will be our tau max or maximum shear stress point. The maximum point here which we marked, which is 450 for this problem, is also called as the Mohr's dot. Now with that, we can move on to the next problem. Now given here is a thin walled pressure vessel and it contains liquefied propane under the pressure of 210 megapascal and it's transported at 100 degree Fahrenheit. We have the inner radius which is 6.16 inches and wall thickness as 0.11 inches. Here we have to determine the principal stresses and overall maximum shear stress at any point on the surface outside and any point on the inside surface. Now all this while, the elements which we were working on were only solid pressure vessels. Here, because we are given thin walled pressure vessel, we have a little bit change in the stress equation we will be using. Now moving on to the whiteboard. So in this given problem, we are supposed to work with thin walled surfaces. Now for thin walled surfaces, the pressure formula changes. It's not the same as we saw earlier. So our sigma 1, one of the principal stresses would be P/R/I by T, wherein P is the pressure exerted on the vessel and Ri is the inner radius and T is the thickness. So we have the thickness and radius here. So with that, we'll be working this problem. In the same way, sigma 2 will be equal to PR, which is pressure into the internal radius divided by 2T, which is exactly half of the first stress. So here, after substituting the values, we'll get sigma 1 is equal to 11,817 megapascal. And same way, sigma 2 will be approximately 5909 megapascal. Now, considering a 3D element, but the first thing we have to find is any point on the surface. On the surface is outside surface, which is the circumferential surface. So, considering any 3D element in the circumferential surface, so we'll consider sigma P1, sigma P2 as the values which we found. But when it comes to the third value, which is sigma 3, we can say that it's going to be 0. So basically, sigma 1 is going to be 11,817 and sigma 2, which is the perpendicular value for sigma 1, is going to be 5909. But because this is the outer surface, the third sigma value is going to be 0 because there is no pressure exerted on the outer surface. Pressure is exerted only on the inner surface, and that too on the inwards direction because it's a pressure exerted by the liquid. So basically sigma 3 is 0. For better understanding, I'll write external here, which is the first question which we are addressing. So this is the first question which we are addressing. Now, if we take the sigma maximum value, it's going to be 11,817, and sigma minimum value is going to be 0, and sigma intermediate value is going to be 5909. And as for the Mohr circle, so first we'll draw the coordinates and we'll give it tau and sigma. So our first value, which is minimum value, is going to be 0, and the maximum value is going to be 11,817. So we can draw a circle for these two values. Our next step is to figure out the tau max value. So for tau max, we know the formula, which is sigma max minus sigma minimum divided by 2. And we know that the minimum value of sigma is 0. So 11,817 divided by 2 is going to give us 5909. So 5909 is the same as our sigma intermediate value. So for this problem, the intermediate stress will be our maximum shear stress, going to be our tau max. With that, we'll go to solving the second statement, which is any point on the inside surface. So as I said earlier, pressure due to a liquid is always inwards, and we know that this is inside the pressure vessel. So we'll write inside for better understanding, and we are solving the second statement. And because there is an inside pressure or inside stress, we can call it sigma x, which is equal to minus 210 MPa. You can call this sigma x or one of the stresses, which is sigma 1. So we'll call this sigma 1. Again, sigma 2 is going to be 5909, and sigma 3 is going to be 11,817 MPa. We got these because we have already solved for this in the previous point. The only new stress which we have got here is the sigma 1, which is minus 210 MPa. And when we take for minimum and maximum and intermediate stresses, we'll get that sigma maximum is going to be 11,817 as always. Sigma minimum is going to be minus 210 MPa, which is the pressure inside the vessel that is exerted by the liquid. And then sigma intermediate is going to be 5909 megapascal. And if we have to mark these values in this 3D element, then we'll quickly erase these two arrows, because we know that inside the vessel, the pressure exerted by the liquid is inwards. So this will be inwards, and it's 210, and the outwards pressure would be the same, 11,879 and 5909. Now, as for tau max value, we know tau max is equal to sigma max minus sigma minimum by 2, which is equal to 11,817 plus 210 divided by 2, and we'll get tau max value as 6013.5. With that, if we have to work with our Mohr circle, so this is going to be our vertical coordinate line and this is going to be our horizontal coordinate line. So let this point be our minimum point, which is minus 210, and this point be our maximum point, which is 11,817, also called as the Mohr's dot. And if we have to draw a circle, it's going to be the biggest circle. Now we know the value for tau max and we also know the value for the intermediate point. We'll quickly plot the intermediate point, which is 5909, and our tau max will be 6013.5. So this will be our tau max value. With that, we can plot the rest of the circles. The first circle, which will be governed inside minus 210 and 5909, which is this. And the second circle will be from 5909 to 11,817. Now this will be our Mohr's plot. And with that, we come to the end of this session. So in this week, we learnt about stresses in certain directions which can have completely different stress components acting on them when an applied load results in the rotation of their element. We also came across calculations for the same using principal plane equations, and we did the calculation for both normal stress and shear stress. So we defined the calculations in two different methods. One was the principal plane equation. The second was the Mohr circle. We also did problems relating to it. And we learnt about the concept of absolute maximum shear stress. And finally, we ended this session by solving few problems about absolute maximum shear stress. See you with another concept in the next week. Thank you. The third week of the Strength of Materials course. This week, we'll be seeing about bending, deflection and torque. Last week, we learnt about principal stresses and Mohr circle. We also saw a few problems that are related to principal stresses and Mohr circle. The table of contents for this week would be a typical beam, supports, loads, beams, internal forces, bending, deflection, torsional deformation of a circular shaft, and torsional formula. The learning objectives for this session would be to learn about a typical beam and its uses. We'll also go through different types of loads and supports that a typical beam would have on it. Then we'll learn about shear force diagram and bending moment diagram with few plots. We'll also see problems related to it. We'll also go through important concepts like bending, deflection and formulas related to it. Finally, we'll end this session with learning about torsion on a circular shaft, and we'll also see about torsional formula, and we'll work on a problem that is related with torsional formula. Now we look at a typical beam. A beam is a versatile structural element, that is, it can be used in many different areas. Beams primarily resist loads applied laterally to the beam's axis. The mode of deflection in beams is bending. Typical examples of beams are RCC buildings, steel trusses, and vehicle axles. If we can see in this figure, which is in the right side, as shown in this figure, the loads carried by a beam are generally transferred to columns, walls, or girders. These structural members, like columns, walls, or girders, then transfer these loads to adjacent structural members to equally distribute the received load. Next, let us look at parts of a typical beam. So what we see here is the front elevation of a beam. We can also call it as the front projection of a beam. This beam rests on two supports at both the ends. Because it is resting on two supports, it will create two support reactions, and these support reactions are termed as R1 and R2. The span of the beam is between these two supports, and this span can also be called as the total length of the beam, which is L. The longitudinal axis cuts the beam lengthwise. Same way, there is one more axis, which is the transverse axis that cuts through the cross-sectional area A dash. In the right side, we can see that the cross-sectional area is given as a rectangle. In this rectangle, there are two more elements. One is the breadth B and the height H. Now, our important variables to note for a beam are span L, breadth B, and height H. The next comes our weight. When we have a load acting on the longitudinal axis of a beam, which is along the transverse axis, this load can be represented as weight, which is W. For some information, the cross section of a beam historically used to be squares or rectangles and were made of stones. Nowadays, these are also made of metals and combination of wood and metal. Sometimes with advances in engineering, mechanics and processing methods, we have developed beams with different cross sections like H beams, I beams, L beams, T beams and double T beams. These new and improved shapes have better load bearing capacities and also better stiffness. Next, let us look at support and support reactions. A structural support is a part of a structure or a structural membrane that provides necessary stiffness and strength in order to resist internal forces. These forces can be forces of gravity or lateral forces that can be caused by gush winds. Now, supports will help guide these loads safely to the nearby membranes that can be used to distribute these loads. A beam is subjected to vertical loads that needs to be transferred below. This is where supports come into play. So basically, supports offer stability and allow movements in some desirable directions. Also, supports can be used to connect elements with the beams. Next, we look at what are the common types of supports. The common types of supports are roller pinned, fixed and simple supports. So the first we will be looking at is the roller support. In roller support, translation is allowed in one direction. Translation is the motion by which a body shifts from one point to another. For example, translation motion is the motion of a bullet fired from a gun. In roller supports, rotation is allowed. Thus, allowable movements in a roller support are horizontal movement and rotational movement. However, there is no movement in the vertical direction. Thus, the number of reactions is 1, which is in the vertical direction. Movement is restricted only in the vertical direction as we saw earlier. Thus, here we can see that we have one reaction which is RV in the vertical direction. Also, horizontal and rotational reactions are 0. Roller supports are commonly depicted as shown in the figure. Some examples of roller supports are rubber bearings, rockers, etc. The next type of support is a pin support. This is also known as hinged support. Pin support does not allow translation in any direction. That is, there is no movement in the horizontal or vertical direction. However, rotation of the beam is allowed. Thus, the allowable movement is only rotation while there is no vertical or horizontal movement. Thus, the number of reactions here are 2. One vertical component and one more is horizontal component. Some common examples of pin supports are bolts, pins and connections and trusses. Another example of a pin support is the human elbow. If you can feel a human elbow, it can be extended and flexed or rotated, but you cannot move your forearm left to right, which is actually translation motion. However, a single pin support cannot completely restrain a structure and at least 2 supports are needed to resist internal moments. The next type of support is fixed support. In this type of support, no translation motion or rotation motion is allowed. Thus, the beam cannot move along the horizontal axis or the vertical axis. It also cannot rotate. Because there is no allowable movement, it might be vertical, horizontal, or rotational. This kind of a support has 3 reactions. One is the vertical, which is RV, second is the horizontal, which is RH, and the third one is the moment, which is M. Fixed supports are generally seen in column to beam connections. They are also seen in cantilever beams, where having a single support is beneficial. Next, we look at loads. What is a load? A load is a force or acceleration that is applied to a structural or mechanical element. It will cause stress, which causes deformation and displacement on the object. In this figure, we can see a rope bridge as the person walks over it. So by definition, it will bend or deform. And loads can be of 2 types. One is static and the other is dynamic loads. Static loads are constant over time, while dynamic loads are variable or moving loads. The other classification of loads is the spread. Spread of loads is the distribution of loads on the structural element. Few examples for all these loads can be given as: for static loads, these are basically dead loads because they are not growing over time, but they are constant over time. And examples of dynamic loads would be live loads and environmental loads. When it comes to the spread of loads, which is basically how they are spread out on a structural element, the first type of load are concentrated loads. These act on relatively smaller area of the element. Thus, they are known as point load. Point loads are applied to a concentrated point on the support. An example would be a person standing at the free end of a diving board. Another common example is a motorcycle resting on the ground. The load of the motorcycle is distributed on 2 load points, that is each wheel. Now these can be considered as point loads. Point loads are depicted using W, which is basically capital W, and the unit is kilonewtons. The next type of loads are uniformly distributed loads. These are loads that are uniformly distributed over a large area of the element. In other words, the magnitude of the load will remain uniform throughout the whole element. One of the example of a uniformly distributed load is a wall that is sitting on a beam. For example, the wall here, its weight is evenly distributed over the beam under it. Another example is the self-weight of a beam, which is uniform for a beam of even cross-section throughout its span. In the left side image, if you can see, this is the beam and the self-weight of the beam will fall over it and the load is distributed uniformly. Like how we saw earlier, the load is depicted as W and the unit is kilonewton per meter. The next type of spread load is called as uniformly varying load. In this, the magnitude of load will uniformly increase or decrease over the given area. Thus, it has zero intensity at one end and a fixed value at the other. This type of load is also known as a triangular load, as the shape of the load that is applied to this beam will now be triangular. Examples of uniformly varying loads are stairs and water pressure on a water tank. As we already saw, uniformly varying loads are depicted using triangles, with one end having 0 and the other end having a magnitude of W, which is also represented using a unit kilonewton per meter. Uniformly distributed loads and uniformly varying loads are difficult to resolve when they are used in large systems. Thus, they are usually converted to point load. A point load is an equivalent load that is applied to a single point. This can be data mined by calculating the total load over the object's area and attributing the entire load to its center of gravity. For a uniformly distributed load, which is UDL, we will take the area of a load, that is load per meter or kilonewton per meter, and multiply it by the span of the load, which is L. The equivalent valid load, which is capital W, now acts at the center of gravity of the rectangular load. And this center of gravity will be at L by 2, which is half of the span. Similarly, the triangular uniformly varying load is the area of the load triangle, that is, load per unit meter or kilonewton per meter multiplied by the span L multiplied by 1 by 2. We do this here because we know that area of triangle is half of length into height. Now we know that the length is the span, which is L, and here our height is W, small w. So here we take the area of the triangle, which is 1 by 2 into W into L. Thus, the equivalent load capital W will now act at the center of gravity of the triangle, which is L by 3 from the maximum value. Thus, for uniformly distributed load, which is UDL, W is the equivalent point load that acts in this center of gravity of the span L, which is at L by 2. Similarly, for UVL, which is the uniformly varying load, due to its triangular shape, the equivalent load W will be again acting in the center of gravity, which is L by 3 from the 0 position. Finally, let us look at beams. A beam is a structural element that is used in an engineering environment to provide a safe and efficient load path. These beams support the load by resisting beam bending under the load's pressure. We will look at the definition of a beam and how they are classified based on the type of a beam. We know that a beam is a structural element. It can be straight or curved. It can be homogeneous or composite. That is, it can be either made of the same material or a composite of two materials. Beam can have a constant cross section or be tapered. A simplified beam for ease of calculation is considered to be straight. Also, it is assumed that the deformation of the beam will be in linear elastic zone of the stress strain curve. We will also assume that any deflection due to loading will be small. One dimension of the beam is significantly larger than the other two dimensions. So here, span of the beam is larger than the breadth and height of the beam. By span we mean L, and breadth is B and H is height. Beams typically have loads that act in the transverse direction, that is perpendicular to the length of the beam. This load can be depicted using W. The beam is also supported at few different points. These points are called supports and are depicted using R, which are the reaction forces due to the support. Let us look at the types of beams based on their support conditions. The first type of beam is called a cantilever beam. These beams are fixed at one end and free at the other end. Examples of cantilever beam can be seen here in the right side image. In the right side image, there is an overhanging in this building. So this support is called as a cantilever support. The image on the left side shows us how a typical beam is shown as a free body diagram in a cantilever beam. As we saw earlier, there is one fixed end and one free end. The fixed end will have three reactions. So these three are the vertical reaction, horizontal reaction and the moment. The free end will not have any reactionary forces as it is not restrained in any manner. The second type of beams are fixed beams. These are beams that are fixed at both ends. Since these beams are fixed on both ends, they will have two vertical reactions, two horizontal reactions and two moment reactions. The next type of beams are simply supported beams. Simply supported beams are simply supported at both the ends. These two supports may be hinged, pinned or roller types. An example of a simply supported beam can be a bridge girder that is resting on columns at two ends. Since there is only restriction in the vertical direction, two reactions are observed in simply supported beams. A vertical reaction force at each support. So for this topic, we will be looking at how to calculate internal forces that are generated because of loading. The internal forces that exist in beams are shear force and bending moment. We will learn how to calculate them and plot them graphically. These graphs are called as shear force diagrams and bending moment diagrams. They can also be shortened as SFD and BMD, wherein SFD is shear force diagram and BMD is bending moment diagram. First, let us look at what happens when a beam is loaded. When a beam is loaded, it will deform, that is, it will bend in the direction of the load. When this bending occurs, the beam will experience internal forces. Two internal forces which a beam will experience at this point would be shear force and bending moment. For shear force, let us assume that we have a beam which is supported on two ends by supports. The support reactions are depicted. We can visualize this scene in this right side diagram. So there is a beam and then it is supported in both the ends. The support reactions are depicted using R1 and R2. Two loads W1 and W2 are also acting on this beam. These loads are gravity loads or downward loads. Shear force is the force acting in a direction parallel to the cross section of the beam. Thus, shear force will act either downwards or upwards across the cross section of the beam. Shear force is the sum of all vertical forces on one side of a section. Let us assume that we have a section x dash across the beam. Shear force is the sum of all vertical forces on either side of this section. The sign convention for shear force will depend on the direction of the force and the side of the section. This figure gives us the sign convention for shear force on the left side and the right side of the beam. Downward forces or gravity load on the left side of the beam are negative, while positive or upward reactionary forces are positive. Similarly, upward reactionary forces on the right side of the beam are negative, while downward gravity loads are positive. Thus, if we were to calculate the reactionary forces or the shear force for the left side of the beam, we can calculate it to be minus W1 because it is downward force on the left side plus R1 because it is a positive force on the left side. Thus, the shear force for the left side of the beam is minus W1 plus R1. Similarly, on the right side of the beam, the gravity force is positive and the reactionary force is negative as we discussed earlier. So, here the equation will be W2, which is positive W2 plus W2 minus R2. Generally, shear force is depicted using Newton or kilonewton as its unit. Now, let us look at what a moment is. Moment of a force is a measure of its tendency to cause a body to rotate about a specific point or axis. Let us assume that we have a section. This section is a beam, or let us assume that it's a cantilever beam. The cantilever beam is as given in the diagram. When a load acts at the end of this point, this cantilever beam will tend to rotate along a fixed point which is given in the second diagram. Now this is called a moment. Moment will develop when the force causes the body to twist. Moments are formed when force does not pass through the center of gravity of the body. If the force was acting along the line, this body would not rotate and does not have a moment. However, as this force causes this portion of the beam to rotate, it causes a moment. This is different from translation motion or movement in the direction of the force. Next, we look at bending moment. Bending moment is the tendency of a force to rotate about a point, or it is the turning effect that is produced by the force. Bending moment is thus calculated to be force into the distance from the location of the moment. Let us assume that we have a beam that is supported on two sides by the reactions R1 and R2. Thus, reaction forces R1 and R2 act upwards. We also have a downward gravity load W. This gravity load W is acting on the span of the beam. Now, the span of the beam is L. Now, let us assume that there is a section x dash across the cross section of the beam. This section is at a distance D from R1 and a distance L minus D from R2. Let us also assume that W1 acts at a distance x from x dash. Let us also assume that W1 acts at a distance x from xx dash. Now, when we look at the sign convention for bending moment, a downward load produces a positive bending moment and an upward load produces a negative bending moment. The sign of the moment is opposite to the direction of the bending moment that causes downward bending or sagging, and negative moment causes upward bending or hogging. Any load that tends to cause sagging in the beam will be considered to have positive bending moment, while any load that causes hogging in the beam will cause negative bending moment. Thus, if we were to calculate the bending moment at section XX for the left side of the beam, we would calculate R1, which causes sagging to be positive. So, which means that R1 into D, while W1 causes hogging. Thus, it is a negative moment. Thus, the net moment at section X dash is R1 into D minus W1 into X. Similarly, if we were to calculate moment on the right side, it would be R2, which causes sagging again, thus positive. So, R2 into L minus D, which is the distance from the section XX. Now, let us look at shear force and bending moment diagrams. Shear force and bending moment are internal forces on the beam. These internal forces act over the entire length of the beam. They can be graphically represented also. These graphical representations are called as shear force diagrams SFD and bending moment diagrams BMD. Let us assume that we have a beam with loads acting on it and a section XX which is given. We can calculate shear force and bending moment at each point across the span of this beam and plot it. This will give us the variation of shear force and bending moment across the length of the beam. This will help us see how the entire beam will respond to it. So, to calculate these, we will see an example. So, from this example, let us see how to calculate shear force and bending moments in beams. Let us take a simply supported beam. The beam is supported at two ends on two simple supports 1 and 2. The beam is loaded with a concentrated point load W1 and a uniformly distributed load W2. The span of the beam is L. The value of W1 is 10 kilonewton and the value of W2 is 1 kilonewton per meter. The 10 kilonewton load acts at 3 meters from the support, while the 1 kilonewton per meter a uniformly distributed load acts over a length of 4 meters from R2. The span of the beam is 10 meters. Knowing these values, we have to calculate R1 and R2, which are the support reactions. Now, to see how it is done, we will assume that the beam system is at equilibrium. This means that the net shear force inside the beam and net bending moment inside the beam are equal to 0. Knowing this, we can now calculate the reactions and moments within this beam. And the first step is to resolve the uniformly distributed load into a point. This is done by multiplying the intensity of the load, which is 1 kilonewton per meter, by span over which the load acts, which is 4 meters. 1 kilonewton per meter multiplied by 4 meters gives us 4 kilonewton. This 4 kilonewton concentrated load will now act at the center of gravity of this load system, which is at 2 meters. Thus, the concentrated point load of 4 kilonewton acts at 2 meters from R2. Knowing this, we will assume that the net shear force within the system is equal to 0. This means that the upward loads are equal to the sum of the downward loads. Thus, R1 plus R2, which are both upward loads, will be equal to 10 plus 4 kilonewton, which are the downward acting loads. So, from that, we can also tell that R1 is equal to 14 minus R2. Our next step is assuming that the net bending moment within the system is also equal to 0. This means that the bending moment at any point on this beam is equal to 0. Let us assume that moment at R1 is equal to 0. Knowing this, we can plot the following equation. R2 into 10, R2 is the reaction force at the second support, into 10, which is the distance at which R2 acts from R1, is equal to the forces on opposite sides or forces that are acting downwards. And for this we can say that 10 into 3 plus 4 into 8. So therefore from this calculation R2 will be equal to 6.2. So finally to get R1 we can simplify this equation, we can simplify this value in the first equation where we found that R1 is equal to 14 minus R2, and finally we will get the answer R1 is equal to 7.8. So R1 will be equal to 7.8 kilonewtons. Thus we now know the values for both R1 and R2. Let us now plot the shear force diagram for the simply supported beam. Shear force units are in kilonewton. The shear force at R1 is equal to 7.8 kilonewton. This is depicted by the upward positive line. The shear force does not change as long as there is no change in force across the beam. Thus the shear force remains constant until the next change in force occurs. This occurs at W1, which is 10 kilonewton acting downwards, or it can also be called as a negative force. Thus the next shear force at W1 is equal to 7.8 minus the negative 10 load, which is 10 kilonewton, which gives us negative 2.2 kilonewton. Again shear force remains constant as long as there is no change in the load. As soon as we reach W2 or the uniformly distributed load, the shear force will now reduce uniformly. Over this 4 meter span, the shear force will reduce at an intensity of 1 kilonewton per meter. Thus the net reduction in shear force is equal to 4 into 1 kilonewton per meter. This gives us negative 4 kilonewton change. Thus the next net force at the end of the uniformly distributed load is equal to minus 2.2 minus 1 into 4, which is equal to 6.2 kilonewton load. Again in this area we have a positive 6.2 kilonewton load acting at R2. This is depicted by the second red line. Thus this figure gives us the variation in the force across the beam. The positive portion of the shear force diagram are given in blue color, or you can say violet, and the negative portion is given in orange color. So with this we can find the distinct difference between the negative and positive portion. Our next step is to plot the bending moment diagram for the simply supported beam. The net bending moment at the ends of a simply supported beam are equal to 0. We know this as the simply supported system has only one vertical reactionary force, while the horizontal reactionary force and bending moment are equal to 0. This is what we saw earlier. So with this we know that M1 and M2, which are the bending moments at the reaction supports, are 0. Our next step is to calculate the bending moment at W1, or where we have 10 kilonewton load. We can calculate the net bending moment on either side of this section. Thus for sake of simplicity we will take the left section of the beam. The left section of the beam as in all the loads that are acting at the left section at W. Thus MW1 or the moment at W1 is equal to 7.8 into 3. So MW1 will be equal to 23.4. So basically the net bending moment at W1 is equal to 23.4 kilonewton. Similarly, we will now calculate the net bending moment at W2 or the starting point of the uniformly distributed load. Similarly, we will again take all the loads that are acting on the left section of the beam. Thus MW2 will be equal to 7.8 into 6 minus 10 into 3. So our net bending moment at W2 will be MW2, which is equal to 16.8 kilonewton. If we connect all these points, we will get the bending moment diagram for the simply supported beam. Since this entire section is positive, we will be depicting the bending moment diagram using the violet color. Now, by combining the shear force and bending moment diagrams and placing them in the same graph, we can see the simply supported beam with all the loads and distances and other variables marked here. We have the shear force diagram showing the maximum and minimum shear forces all in kilonewton. Then we have the bending moment diagram, which is all shown in kilonewton meter. Shear force and bending moment diagrams are important in structural analysis because they give us the points of maximum shear stress. Thus, we can see that the maximum shear stress that this beam will sustain is at the support reactions 7.8 and minus 6.2 kilonewtons respectively. Similarly, it also gives us the points of maximum bending. In the bending moment diagram, here we can see that the maximum bending occurs at 10 kilonewton load value. This means that at this section the beam will experience maximum bending. This gives us an idea of what kind of material can be used in which section of the beam and if there is any necessity of adding reinforcements in any of this section. Our previous example was a simply supported beam. Now, our previous example was a simply supported beam. Let us take the example of a cantilever beam this time. A cantilever beam is fixed on one end and free on the other, as we saw earlier. Since this end is a fixed end, we have three reactionary forces, and those reactionary forces would be RH, which is the horizontal reactionary force, RV, which is the vertical reactionary force, and a moment, which is M. This is because in a fixed end, the beam is restricted from motion in both horizontal and vertical directions as well as rotation. Thus, we have these three reactionary forces similar to our simply supported beam. We will have the same span and distance of both loads, the concentrated point load acting at 10 kilonewton at a distance of 3 meters from the fixed end and the 1 kilonewton load that acts on a 4 meter span from the free end. Our next step is to calculate the reactions and moments in this beam. We know that the net force within the beam is equal to 0 and RV, which is the upward load, should be equal to the net downward load. And this is equal to 10 kilonewton plus 4 kilonewton. So, RV here is equal to 10 plus 4 kilonewton. Again, this 4 kilonewton is the result of 1 kilonewton per meter load that acts over 4 meters. So, which is 1 into 4. That way we got RV equal to 14. Let us start with the RV or the fixed end. We have a maximum shear force of 14 kilonewton, which is positive 14 kilonewton, and we can say that it's acting upwards. Thus, we have 14 kilonewtons here, and since there is no change, the shear force remains constant until there is a negative 10 kilonewton force. Thus, the next shear force at this point, which is AW1, is equal to 14 minus 10, which is equal to 4. Again, shear force remains constant as long as there is no change in the load. As soon as we start the uniformly distributed load section, the shear force reduces at an intensity of 1 kilonewton meter for a span of 4 meters. Thus, the net reduction in shear force from W2 to R2, which is to the end of the beam, is equal to 0, that is 4 minus 4 into 1 kilonewton. The next shear force at the free end is equal to 0. We already know that cantilever beam is fixed on one end. The fixed end prevents any rotation in the beam. Thus, there is a bending moment component that occurs at the fixed end. If we are to calculate this bending moment, this would equal to the moments exerted by all the forces on the right side of the beam. Bending moment units are in kilonewton meter in this figure. Since we know that there is a bending moment component at the fixed end, we can start calculating the bending moment from the free end. We know that bending moment at the free end will be equal to 0 as there is no reactionary components beyond this point. Our next step is to calculate the bending moment at W2. This is done by resolving the uniformly distributed load into a point load as 1 kilonewton. 1 kilonewton per meter multiplied by 4 meters, which gives us a point load of 4 kilonewtons. This 4 kilonewton load acts at the center of gravity of this load system, which is at 2 meters. Thus, we can calculate MW2 to be equal to minus 1 into 4, which is 4 kilonewton load acting at a distance of 2 meters. Thus, the moment at W2 is equal to minus 8 kilonewton meter. However, as this is a uniformly distributed load, the shape of the curve will be a parabola. Our next step is to calculate the moment at W2. This is equal to minus 1. Our next step is to calculate the moment at W1. This is equal to minus 1 into 4 into 5. Here 4 is the resolved or uniformly distributed load multiplied by 5, which is the distance from the section, that is equal to 3 meters plus 2 meters, or the distance at which the uniformly distributed load will be resolved into. This is equal to minus 20 kilonewton meter. Similarly, the moment at the reactionary forces, which is basically at the fixed point, is equal to minus 10 into 3, which is the distance at which the 10 kilonewton load will act, minus 1 into 4 into 8. So MRV is equal to minus 62. So it's basically minus 62 kilonewton meter. This bending moment is due to downward acting forces. Thus, the entire bending moment values are negative values. For differentiation, we have depicted this in orange color. If we now combine the shear force and bending moment diagrams for the cantilever beam, we can plot the shear force and bending moment, and we can say that shear force is completely positive within the given region, and also bending moment is completely negative within the given region. And we have to take note that shear force is depicted in kilonewton while bending moment is depicted in kilonewton meter. Examples, we might have noticed that the different loads like point loads and uniformly distributed loads are depicted differently on our shear force and bending moment diagrams. This is because different loads are depicted with different types of mathematical functions. These functions can be linear or parabolic or hyperbolic equations. In the next few slides, we will be seeing how each of these loads are depicted. So the first will be point loads. Let us assume that we have a simply supported beam on which two loads are acting. As for the shear force diagram, the point load will be depicted using a linear function where y is equal to shear force value. At the same time, x is equal to the span, basically the span of the beam. Thus, if we look at it mathematically, mathematical equation would look something like this, where y, the shear force, is at some value for the entire span until there is a change in the value. While BMD is also a linear function where y is equal to x, that is shown in the second figure, where we have y value equivalent to the x value, which is the span. This is exactly why in this figure our BMD plot has a tilt in both the areas. This is exactly why our BMD plot has a tilt which is equal in both the regions. The next type of loads that we will be seeing are uniformly distributed loads. The shear force over the span of the beam will reduce as per the intensity of the beam. Thus, for a shear force diagram, the shear force is depicted using the linear functions, and on a graph it would look like this. So basically it would be a line that is tilting where y is equal to x. The span as seen will have a gradual reduction behavior when it comes to shear force. As far as bending moment diagram is concerned, it is basically a parabolic function. Parabolic functions have the following mathematical equation of y equal to x square. Thus, the shape of the curve would be a curve with the function y which is equal to x square as shown in the figure. Thus, for uniformly distributed loads, the shear force would reduce according to the intensity of the load and the bending moment would increase by parabolic function. Next, we will be looking at uniformly varying loads. For a uniformly varying load, the load will vary from an intensity of 0 at one end to maximum at the other. Thus, for the shear force diagram, a parabolic function would be used where y is equal to x square. The curve would thus look something similar to this. While the bending moment diagram would be depicted using a cubic function wherein y is equal to x cube. This function is shown using the second diagram. Next, we will be looking at bending. The definition of bending is to curve out of a straight line or position. That is, it is a movement that causes the formation of a curve. This happens when a load is applied to a straight element which leads to its curving. In this section, we will look at how to calculate and derive the bending formula. Let us look at what happens when a beam is loaded. Here we have a simply supported beam on which there is a point load acting at the midpoint, that is L by 2. L by 2 is half of the span of this beam. The top part of the beam is under compression while the bottom part of the beam is under tension. This is because the top part of the beam is getting compressed or reduced in length while the bottom part of the beam is in extension or elongation. The direction in which the beam will bend depends on the type of load, and in this case, where we have a downward or gravity load, sagging occurs in the beam. Sagging is when the top of the beam sink under a load with a concave curvature. Hogging will occur when an upward or a pulling force is applied to this beam. It will lead to convex curvature. Hogging occurs when there is a reactionary force or pre-stressing is involved. We will learn more about pre-stressing in the upcoming modules. And also we will be calculating and deriving the bending formula to do that. But before that, we need to know what a neutral axis is. So let us assume that a beam is placed under a load. In this case, the beam is under sagging conditions. Thus, the bottom half of the beam is under tension, depicted in green, and the top part is under compression, which is depicted in orange. The bottommost part of the beam will be under the highest amount of tension, while the topmost part of the beam will be under the highest compression. Now let us assume a section of the beam, that is one portion of this beam that is subjected to the load. When we plot the cross section of the beam and the stress across the cross section, first is tension, and we know that tension is maximum at the bottom. So if we can see here, the tension is maximum at the bottom and then it keeps reducing until it reaches to one point where the value of tension is 0. The same way, if we take the highest compression value, when we go down the y-axis, the compression value travels till it reaches the tension region, and when it reaches this point, again the compression value will also be reduced to 0. This point where both compressive force, which is Fc, and tensile force, which is Ft, is 0, is called as the neutral axis. Thus, the neutral axis is the axis where stress is 0. If we have to draw the neutral axis across the beam, then this is where it will be. Now, let us take a simply supported beam. In this beam, we will take a section AB that experiences pure bending in the tension zone. This section is at a distance y from the neutral axis. When this beam is placed under load, this section will bend, and in this case, the bending radius will be r, and theta is the angle of bending. We can call the bend section as A dash and B dash, while y dash is the distance of deflection or bending, that is from the neutral axis. Here, the value of theta is very small in reality and it will tend to 0. Now, let us look at the original unbent section of AB. The original length AB will be equal to r theta. This is derived as follows. Cos theta, which is adjacent by height, is equal to r by AB. That is the radius of the bend section divided by the original length AB. Theta tends to 0, which is in reality. We can say that theta is a very small value and cos theta as a very small value is equal to 1. Thus, AB is equal to r theta. Now, let us look at the bend section. the bend section is A dash B dash. This will be equal to R plus Y into theta. Again, this is because we know that cos theta is equal to 1. So, A dash B dash will be equal to R plus Y into theta. Next, when we look at the strain in the section A dash B dash, epsilon will be equal to delta L divided by L naught, wherein delta L is the change in length and L naught is the original length. The change in length is the difference between the final length and the original length. Here we know that the final length is R plus Y theta and the original length is R theta. So from that we can calculate R plus Y theta minus R theta divided by R theta. So from calculations we will get epsilon value as Y by R, wherein Y is the distance from the neutral axis to the bend section, which is A dash B dash. Next, when we take stress in A dash B dash, it's sigma equal to F. Next, when we take Young's modulus, E is equal to epsilon divided by sigma. We know that epsilon is Y by R and sigma is F. So from that, E will be equal to Y by R divided by F. Thus, to derive the simple bending equation, E by R is equal to F by Y, where E is the Young's modulus, R is the radius of bending, F is the stress in the element and Y is the deflection in the element. Let us now see what moment of resistance is. Moment of resistance is when this beam is placed under a load. When this beam is placed under a load, it is under both tension and compression. This forms a couple across any cross section which has a moment. The compressive force Fc generates an anti-clockwise moment mc, while the tension force Ft generates a clockwise moment mt. The moment of resistance within this section is equal to the net bending moment, that is equal to mc, which is the compressive moment, plus mt, which is the tensile moment. So here we can see that mr is equal to net bending moment, which is equal to mc plus mt. Now, assuming that we have a very small area which is depicted by del A, this area is at a distance of y from the neutral axis in the compressive zone. The stress on this element can be given as F, which is equal to E by R into Y. Now, this value is something which we have got from the bending equation. Next, the force on this element will be equal to stress multiplied by area. We know that force is equal to stress multiplied by area, and we got the stress here, which is E by R into Y into the area del A. As we've seen the force on the element, next we'll see moment about the line NA. Now this is also from the element. From the element is in a distance of Y from the line NA. And if we have to find the moment, we know that the formula for moment is force into distance. We know that force is E by R into Y into del A, and the distance here is Y. So finally we get a moment of E by R into del A into Y square. Next, for the moment of resistance, the moment of resistance can be given as the sum of all moments on the element. So right now we can say that sum of all the compressive moments on the element, because this moment is on the compressive side. Now, moment of resistance is equal to the summation of E by R Y square del A. Here we know that E by R is a constant. So placing E by R left of the summation, we can call Y square del A as I, or the moment of inertia. We can call sigma Y square del A as I. We can denote sigma Y square del A as I, which is moment of inertia. So basically moment of inertia will be equal to the summation of Y square del A. Finally, from whatever we have derived earlier, the moment of resistance equation will be M divided by I, which will be equal to E by R, wherein M is the moment of resistance, I is the moment of inertia, E is the modulus of elasticity, and R is the radius. This moment of resistance equation is also called as Bernoulli's bending equation. So the Bernoulli-Euler bending equation is the relationship between the bending moment, moment of inertia, elastic modulus and radius of bending, stress and distance of element from the neutral axis. From the earlier equations, when we take all these into account, our Bernoulli-Euler bending equation will be m by I, which equal to E by R equal to F by Y. Next, we look at section modulus. We know that m by I is equal to F by Y. We got this from the Bernoulli equation. Thus, F, or the stress in the element, is equal to the moment of resistance divided by the moment of inertia multiplied by Y, which is deflection. Maximum stress in this element will occur at the end. That is when Y is at its maximum limit. Thus, F max will be equal to m by I Y max. M is equal to I divided by Y max. This we have seen in the previous equations. So, by substituting these values inside the F max equation, we will get F max is equal to Z into F max, where Z is the section modulus. Thus, section modulus is equal to the moment of inertia of cross section about the neutral axis divided by the maximum distance from the neutral axis, that is Z is equal to I by Y max. So basically, section modulus is used to calculate the safe moment of resistance for a specific material. The next section will be deflection. Deflection is the measure of how much a beam will bend under a load. Let us assume that we have a cantilever beam with a point load at its end. This beam will bend downwards as shown in the figure. The dotted line shows the curvature of bending that will occur in the beam. Deflection can be expressed in two ways. First is using angle of deflection, that is the angle at which the deflection curve is with respect to the original element. It can also be expressed using distance, where the endpoints of the beam and the distance between them after curvature and before curvature, which is delta deflection, is a crucial part. It can also be expressed using distance, the endpoints of the beam and the distance between them after curvature and before curvature. This can also be given as delta. Deflection is a crucial part of engineering design because too much deflection is an indication of failure. Now, what is flexural rigidity? The moment equation is m by I, which is equal to E by R, and that is equal to F by Y. Let's look at the radius of curvature of beam, which is equal to EI divided by M. Now, EI, which is the multiplication of Young's modulus and the moment of inertia. This is called the flexural rigidity of the element. Now, flexural rigidity gives us a measure of how stiff the material is against flexural bending or curving. In the next few slides, we will calculate the amount of deflection or bending in a curve. We will derive the deflection formula. To do that, let us assume a fixed beam with a point load acting on one end. This beam will curve downwards. This is called the elastic curve of the beam. The slope of this elastic curve is y by x, where y is the vertical axis or the amount of bending and x is the span of the beam or the horizontal axis. Let us assume that the deflection in the beam is negligible. Thus, the radius of bending is as shown. The deflection is delta, which is a very small value since the deflection is negligible. Knowing that, we can now calculate tan theta, which is equal to opposite side dy divided by the adjacent side dx. When we differentiate both these sides, we get d square y divided by dx square, which is equal to secant square theta d theta by dx. So now let us calculate the Euler-Bernoulli deflection equation. From the figure, cos d theta is equal to r by ds, which is adjacent divided by opposite side. Since d theta is a negligible value, cos d theta is almost equal to d theta. Thus, 1 by r is equal to d theta divided by ds. And when we take differentiation, it is equal to d square y divided by dx square into 1 by secant square theta. We know that secant theta is dx secant square theta. After differentiation, it is equal to d square s divided by dx square, which is approximately equal to 1. Therefore, 1 by r is equal to d square y divided by dx square, as we know that secant theta is approximately equal to 1. Now, if we look at the bending equation, m by I equal to E by R equal to F by Y, it can be rewritten as m, which is the moment of resistance, which is equal to Young's modulus multiplied by moment of inertia multiplied by 1 by R, which is the value of bending. Thus, moment of resistance is equal to E into I d square y divided by dx square. Since 1 by r is equal to d square y divided by dx square, now using this equation, we can calculate the deflection. From whatever we saw previously, deflection is depicted using delta. Deflection can be calculated by double integrating the previous equation. The equation E I d square y divided by dx square is equal to m can be integrated once. The first integration will give us the slope of the elastic curve, also known as dy by dx. First integration gives us integral m plus c1, where c1 is the integration constant. If we integrate this equation, we will get ei into y, which is equal to double integral m plus c1x plus c2. c2 is the other integration constant. Thus, y, which is equal to the deflection, is equal to double integral of m plus c1x plus c2 divided by ei. Here, m is the moment of resistance, c1 and c2 are the integration constants, x is the distance at which the deflection is measured, and E is the elastic modulus. We can also see that I is the moment of inertia in this equation. Now, using this equation, we can easily calculate the deflection delta at the distance x. Torque can be defined as the moment exerted on a member in an attempt to twist it about its longitudinal axis. The effect it takes becomes a primary concern while designing graph plots, which are found in automobile and machineries. On the right hand side, you can see there is an example of a styrofoam tube in which there are boxes drawn. The left side box is a rhombus and the right side box is a rectangle. Now, when we apply a torque on this styrofoam tube, by torque I mean the right hand goes upwards or twists the tube upwards and the left hand twists the tube downwards. By doing this, we can see there is a change in the shape of these boxes. The rhombus here has a change in its length and breadth. At the same time, the rectangle here has a change in its angles. So by change in angle, it means that this rectangle is undergoing shear stress while the rhombus is undergoing normal stress. But this is exactly opposite when it comes to the previous example which we saw in our previous session, which was the elongation of the glove. In the elongation of the surgical glove, we saw that the rhombus was experiencing shear stress and the rectangle was experiencing axial stress or normal stress. Now, these are the effects of applying torque to a tube. A more digital illustration can be given by considering a shaft made of another material that is highly deformable. Example, rubber. The grid lines that run longitudinally, which are inscribed on the shaft, tend to distort with the application of torque. The distortion often takes the shape of a helix that can be observed to intersect the circular section at equal angles. Additionally, the cross sections of the shaft are assumed to be constant and do not experience any form of bulging or warping. Now, we can easily see the difference between the parallel lines that are running here before deformation and the parallel lines that are intersecting with the neutral axis of the cross section. We have already come across this concept called neutral axis when we were studying about bending and deflection. The neutral axis works the same way here, where it is not changed with whatever torque is given. We also should note that there is a unique distinction for the radial lines. The radial lines can also be seen to remain straight, where rotation can be observed with the deformation due to the applied load. But one more thing which we have to note here is when the twist angle is quite small, the length and the shaft radius can be assumed to be practically unchanged. Next, we'll see what is torsion formula. A shaft which is made of cross section in the form of a circle experiences twisting on applying torque in a way that the shaft's shear strain always remains proportional to its radial distance from the center. This basically means that the increase in the radial distance will result in further increase in the shear strain of a shaft. So therefore, at the highest radial distance, which is the radius of the shaft, the strain is highest, or you can say that the stress is highest. Now here, assuming that the material has linear elasticity and is homogeneous, the torsion formula that can be used to calculate the shear stress is tau max, which is equal to Tr by J. Here, tau max is the maximum shear stress in the shaft occurring, which is always on the outer surface. Now, if we substitute rho in place of R, it means that the shear stress that is happening at any point rho from the center of the shaft or the neutral axis of the shaft. This distance can also be given as rho. But we have to note here that when rho is equal to R, we again get the value for maximum shear stress. Now, we can see the formula here. And in this formula, T is the resultant internal torque acting at the cross section, whose value can be easily determined from the torque diagram. Next, J is the polar moment of inertia, which can also be called as the section property of the given material. R is the outer radius of the shaft, and rho can be the intermediate distance on the cross section. So basically, rho can vary from 0 to R. Some of the common places where we can observe torque are creation of torque in machineries and motors which has twist in them. So basically we know that motors have twist in them, and some other examples are drive shafts, wrenches, seesaws and other places. So we can see that a wrench is tightening a bolt here, and obviously torque is involved here because there is twisting motion. In the next diagram we can see that a seesaw that is having a twisting motion which is fixed at the center. It's kind of rotating about the center, but it's not extremely high rotation. So there will always be an internal torque to balance the rotation at the center. And then next we have a pulley system that is again a control using torque. Next, let us see what shear stress is. Torsional shear stress develops when transmitting a torque from one plane to another. For example, a shaft connecting an electric motor to a pump. Now the main assumptions is that the stress concentrations at connecting devices can be ignored. Now the assumption means that if we have a motor which is connected to two shafts at the end, then the shear stress that is experienced on the motor or stress concentrations that is experienced on the motor due to the connections can be ignored. But other than that, we will be finding the shear stress that is acting on the motor. Now, for equilibrium, if a torque T is applied at one end of the shaft, every cross section must resist the torque. This resistance is basically the reaction force or the reaction torque that is happening against the torque which is applied. This reaction torque can be given as Tr, and it is caused by the shear stress distribution across the cross section. Now, if we take the diagram in the right side, at any radial distance rho, the shear stress is constant. However, as the value of rho increases or decreases, the value of shear stress also increase and decrease. So it's basically proportional to the value of rho. Coming to the force dF, we know that force is equal to stress into area. So dF will be equal to tau rho into dA, where tau rho is the shear stress that is acting per meter, that is acting per meter square on the distance rho. Now dTr will be equal to rho dF, because we know that moment is equal to distance into the force applied. Now we know the value of dF, which is tau rho dA. So we can simplify that value here and we'll get dTr is equal to tau rho dA. Taking integration both sides, we'll get the value of Tr, which is equal to tau rho dA. Next, the same way we can calculate torsional shear strain. From the previous sessions, we know that stress is equal to multiplication of modulus and strain. Here, again we can see that tau C, which is shear stress, is equal to G into gamma C, which is the shear strain. Now G here is the shear modulus, while C here denotes the maximum radial length from the center. Rho denotes the point anywhere inside the radial length. So basically the shear strain at a distance rho from the axis. We know that strain can also be given as change in length by length. Now here again, gamma C, which is actually tan gamma C, is equal to del B divided by the actual length. But for small angles, tan can be negated and gamma C is equal to del B by L. And again, inside the material at a distance rho from the axis, gamma rho is equal to del rho by L. Now for the angle of rotation, which is theta, we know that for the distance C, it is del B by C, and for distance rho, we know that it's del rho by rho. Dividing L in all these equations, we get the formula gamma C by C, which is equal to gamma rho by rho, which is basically after simplifying L here. Now we know that gamma C is equal to del B by L, and the same way gamma rho is del rho by L. And we are substituting these equations. Here we get a relation between gamma rho and rho. This means that for every increase in the value of rho, there is a linear increase in the value of gamma rho too. Now that we got the relation between rho and gamma rho, we'll go into finding the elastic torsion formula. But before finding the elastic torsion formula, we need to address some assumptions. The first one is that the shaft that is undergoing a torque is circular. It has a constant cross section. The value of strain and the value of angle is small. Finally, shear stress and strain have a linear relationship, which is it falls under the proportionality limit. Now for the elastic torsion formula, from the previous slides we know that tau rho is equal to G into gamma rho, and same way tau C is equal to G into gamma C. Substituting these formulas into the relation which we got, we get tau rho by rho is equal to tau C by C. Therefore, again we can say that tau rho is equal to tau C by C into rho. Now, if we recall the formula for torque, which is T equal to integral of tau rho dA, we can substitute the value of tau rho which we found now into this torque formula, and finally we get a simplified version, which is T is equal to tau C by C and integral of rho square dA. Here, the integral of rho square dA can also be called as polar moment of inertia. Now for maximum torque, we take the maximum value of shear stress, which is tau C max, and the maximum radial distance, which is C. At the same time, the same formula can also be possible for a distance rho from the center point inside the surface of the shaft. So tau C will be equal to T into C divided by J, and tau rho will be equal to T into rho divided by J. Next, let us see what polar moment of inertia is. Now, polar moment of inertia can change for a solid shaft and a hollow shaft. We know that J is the polar moment of inertia, and in a shaft with a circular cross section where the thickness of the ring is dou rho and the circumference is 2 pi rho, for this ring we can say that area of the ring is equal to 2 pi, which is 2 pi rho, which is the circumference, into dou rho, which is the thickness. To calculate J for this shaft, from the previous slide, we know that J is equal to integration of rho square dA. Now, taking the area integration of rho square dA and giving it limits 0 to r, if we substitute the value of dA in this equation, we get 2 pi integration of 0 to r dou cube d rho. Now, taking the limits, as for a solid section, we'll get J equal to pi by 2 into r to the power 4 after simplifying the integral. And the same way for hollow tubes, which has inner radius Ri and outer radius Ro, after simplifying the integration, we get J equal to pi by 2 into Ro to the power 4 minus Ri to the power 4. Now, when we come to shear stress distribution, shear is same on adjacent surfaces, which we saw. So, by using the formula for torsion, we need to address the sign convention that goes with the shear stress distribution. We previously saw sign convention when we were working on SFD, BMD and deflection. Now we'll see sign convention for torsion formula. Again, when we use the right hand thumb, when we take a shaft, in the right side and the left side region of a shaft, if the reaction is acting outwards, then the torque is positive. The same way, if the reaction is acting inside the shaft, then the sign convention is negative there. Next, we come to the analysis procedure. The torsion formula can be applied on any material system, and for any material system, this procedure should be followed to find the desired values. The first step would be to address the internal torque. The shaft should be sectioned at a point perpendicular to the axis to calculate shear stress. Now, to calculate the internal torque, we need to take free body diagrams and equilibrium equations, and we move on to the second step, which is section property. Basically, section property is the polar moment of inertia. We already calculated different polar moment of inertia for different type of shafts, and we'll use the exact same equations to calculate the polar moment of inertia for a given cross-sectional area. The next step would be to calculate the shear stress. The radial distance rho should be specified, which is measured from the center of the cross-section to the point at which the shear stress will be calculated. Once the distance is specified, the torsional formula should be applied and the unit should be kept consistent. Now, with this torsion formula, we can find different values. We can find the torque, we can find shear stress and more. But one thing to note here is that shear stress is assumed to always act on the cross section along the direction which is perpendicular to rho. The force created by the stress contributes to the respective torque about the shaft's axis, which has the same direction as that of the internal resultant torque T acting on the section. So this actually means that the direction of the torque created due to force is same as that of the internal resultant torque acting on the section. With that, we'll move on to solving a problem, a very simple problem, wherein we find torque, shear stress and etc. of a shaft. Here we are given two shafts, one is a solid shaft and the other is a hollow shaft. In the problem, the allowable shear stress of the solid and hollow shaft shown is 75 megapascal, which is the maximum shear stress. We are supposed to determine the maximum applicable torque for each cross section and determine the stresses acting at point A on the solid shaft and at point B and C for the hollow one. Now, we cannot do the first step from the analysis procedure because here we don't have any means for the free body diagram or equilibrium forces. Instead, we can go for the second step, which is the section properties. Section properties that can also be called as polar moment of inertia. So each shaft, the solid shaft and the hollow shaft, have different polar moment of inertias. Here Js is equal to pi by 2 r to the power 4 from the formula, and the same way for hollow shaft it is pi by 2 into r o to the power 4 minus r I to the power 4. The polar moment of inertia for solid shaft, after simplifying the values which we know in the formula, is 0.1571 into 10 to the power minus 3 meter power 4. Here 0.1 is basically 100 mm changed to 0.1 meter or converted to 0.1 meter. Same way for hollow shaft, we can see that the outer surface is 0.1 to the power 4 minus the inner surface, which is 0.075 to the power 4. With that, we move on to the first problem, which is calculating the maximum torque. Formula for shear stress is tau max is equal to Tc by J. Here we need to find the maximum torque for the solid shaft and maximum torque for the hollow shaft. Ts is given as the torque for solid shaft. From the formula, tau max is 75 into 10 to the power 6, which is 75 megapascal. And if we substitute values of distance, which is radial distance, and polar moment of inertia for the solid shaft in this formula, we get the torque of the solid shaft, which is 118 kilonewton meter. Similarly, if we substitute the associated values with the hollow shaft, we get Tt, which is equal to 80.5 kilonewton meter. Now, we need to keep in mind that kilonewton meter is the unit of torque. From the problem given, the next statement was for us to determine the stresses acting on different points A, B and C in the shaft. If we see this diagram, point A and point B in the solid and hollow shaft respectively are located in the outermost surface, and we know that the outermost surface is experiencing a maximum shear stress of 75 megapascal. Therefore, point A and point B are also experiencing stress of 75 megapascal. However, we need to find the shear stress that is experienced by point C. For point C, tau I will be equal to Tc by J. Tau I is the stress that is experienced in the inner circle of the shaft. We know the torque of the hollow shaft. We also know the distance, the radial distance from the center point for the inner circle. The inner circle distance is 75 mm and we have converted it into 0.075 meter divided by J. J is the polar moment of inertia of the hollow shaft. From that we get the shear stress experienced in the inner circle, which is 56.2 megapascal. Now this can be the same as the shear stress that is experienced by the point C. With that we come to the end of this session. So to summarize this session, in this week we learned about beams and their properties. We also saw beam as versatile structural elements. We saw some of the examples of beams and supports for beams. Then we came across loads acting on a beam, and we also saw problems that are relating to bending moment diagrams and shear force diagrams. Later, we learned about the concept of bending. We also saw the concept of deflection. We came across various formulas related to bending and deflection. Finally, in the last section, we saw what is torsion and torsion on a circular shaft. We came across torsional formula, derived it, and also worked on a problem that is related to torsional formula. That's it for this week. See you in the next week. Thank you. So this week is all about theories of failure. In the previous week, we learnt about beams and the properties of beams. We also saw and defined that a beam is a versatile structural element. We came across few examples for supports of beams. There was also an overview on loads that are acting on beams and types of loads. We learnt about BMD and SFD, which is basically bending moment diagrams and shear force diagrams. We also solved few problems relating to them. Later we came across concepts like bending and deflection. We also derived few formulas relating to bending and deflection and justified it with examples, and finally we concluded the last session with torsion and its formula with a suitable example. Now, this week, the table of contents is as follows. First, we'll be looking at failure by yielding and fracture. Then, we'll go through ductile and brittle materials. Next, we'll be seeing about yield criteria for ductile materials. And then that will be followed by failure criteria for brittle materials. And we'll end the course with a suitable example. Now, we can go into the course. Let us go into the first topic, which is failure by yielding and fracture. So, in applications, failure is defined by the physical situation. Sometimes, as an engineer, we have to understand what failure is and how we can define failure for certain applications. At times, a small amount of elastic deformation can be considered as failure because it's crossing the yield stress. Whereas, for certain applications, permanent deformation will be considered as failure because it is going into strain hardening, necking, and other aspects. And sometimes, in certain applications, we have to wait till fracture to define failure, and this point is very application oriented. So, first we have to define which type of failure we will be taking as our case to approach this problem. If you see the figure on the right, for ductile materials, there are three phases. Plastic deformation, as we have already seen, the first zone, which is yielding. The second phase is necking, and the third phase is called fracture. And these phases can also be called as yielding, strain hardening, necking, and these three actually comes before fracture. So therefore, for certain material applications, as engineers, we always ideally want it to be lying within the elastic limit, because this is where all our equations can work properly, which is basically the proportionality limit. And with that, we don't want the material to go beyond the elastic limit, which will basically make it a plastic. There are certain applications where even a little bit of elastic deformation will not be allowed. For example, we can take concrete. So concrete has a very small amount of elastic strength, or we can also call it as tensile strength. So hence, the elastic deformation in the tensile zone is something we shouldn't take as a complete value. However, there are some applications for which we can go a little bit into the yielding zone and we can still make that material work. But as engineers, again, we want the failure to be defined at the yielding stress, which is a point where the yielding starts just before the yield point. So we have yield stress now, and with the use of factor of safety, we can make sure that the material doesn't go into fatigue under its normal lifespan. So now, an application's failure is defined by the physical situation of that application. We will compare stress applied to an object with its limiting stress. And when we take a brittle material, as you can see on the right side, very little yielding is experienced, and the tensile fracture will typically hold very large amounts of compressive loads. In the same time, tensile load cannot hold it. So, finally, to sum it up, any material is said to be experiencing failure only when it goes into fatigue, which is when it breaks. So, with that, we can see the common types of failure. Failure in a material can be perceived as the aspect where the material experiences fracture. Now, this is also known as the complete separation of the material into two parts or many parts. Another reason behind failure may also be attributed to excessive deformation, both elastic and inelastic, due to repetitive loading or various other reasons. So, as we saw, there are different types of failures with different types of definitions depending on the application or depending on the material. But finally, the most common types of failure are of three types. The first one is excessive elastic deformation. Second one is yielding failure. The third one is fracture. And as for excessive elastic deformation, this deformation is accompanied by different failure modes. So these failure modes can be stretching, bending or twisting, buckling and vibration. Now these aspects, although are called elastic deformation and it is known to recover, but in practice this material never recovers. So usually there is a very small amount of deformation. Every time a load is applied on a system, there is a very small amount of deformation. And because this deformation is very small, it doesn't really affect the performance of the system, and therefore we term it as elastic deformation. And as a result, we can expect that the material will not fail due to that elastic deformation. However, we all know that there is a particular lifespan for materials and there cannot be any material that stays forever. At one point, it will need to be replaced, changed, or at least serviced. So, even with the little amounts of elastic deformation, every time it is given, the amount adds up. And this accumulation results in huge amount of deformation. Now, with that, stretching, bending, or twisting are basically common types of failures. Now, any material can undergo constant stretching and bending. So, for example, if we take a screw and if we keep twisting the screw for a couple of years, we might notice that there is a problem with the threading of that screw. Now, to repair the screw, we again take it out and then we'll try to repeat the threading process using some other machine on this screw. Now, again, if we keep repeating this threading process on top of that screw or along the screw's axis, then it's going to experience repetitive loads, and due to this, the screw will attain failure. Now, obviously, this is a very common type of failure that the screw will be undergoing, and that comes under stretching, bending, or twisting. Another mode is buckling. Buckling is again a very common but a very important phenomena when it comes to beams or columns. Even though the material is not failing with the loading system, but if there is an actual load, then there is a tendency that it might buckle. So, as engineers, we'll have to make sure that the loading does not result in the buckling of the column. Now, I told that buckling is a very important behavior because when it comes to excessive elastic deformation, although the load which is applied is within the elastic limit, the material might still result in failure due to buckling. So this should be treated as a very important mode of failure. The next type of failure is vibration. Now this is a dynamic property, and in any material or material system, or you can call it a structural system, there will be vibration due to whatever loading or whatever load it is undergoing. Normally vibration is acceptable as inevitable phenomena, but this vibration, when it reaches resonance or when there is excessive amount of vibration, then even when the load that the material undergoes is within the elastic limit, it can still attain failure. And the next common type of failure would be yielding failure. Now, failure due to yielding can be again accompanied with three different modes. One would be plastic deformation at room temperature. Second one is yield stress, and this is a very important design factor. The third one is creep at elevated temperatures. Now, yielding is a common failure type for ductile materials, and whenever the yield stress is reached, the material is defined as it has attained failure. Now, even though the material doesn't completely tear apart, but still when it reaches the yielding stress or crosses the yielding stress value, it means that it has attained yielding failure. So, as designers and engineers, we'll have to make sure that the material which we are designing for doesn't cross the yield stress for a given load. Also, it's very important and critical to understand that yielding can also take place due to plastic deformation. Next, we'll see creep at elevated temperatures. Sometimes, even though the stress is below the yield stress, creep can be a very important factor which we have to consider. Due to elevated temperatures, even within the elastic range, the material can undergo creep, which is again a failure. We'll be looking more at creep at the end of this session. So finally, the next common factor is fracture. So again, failure due to fracture can be accompanied by different modes. The first one will be fatigue or progressive fracture. The second one is sudden fracture experienced in brittle materials. The third is going to be fracture due to stress at high temperatures, and the fourth and final will be ultimate stress, which is again an important design criteria. Now here, as for fatigue or progressive fracture, this is a fracture that takes place in ductile materials. So in ductile materials, the material will first undergo phenomena like strain hardening, necking, and then finally move to failure, which is fracture. But when it comes to brittle materials, it is going to hold for a long time and then suddenly break, which is snap without any kind of indication. The other two, fracture due to stress at high temperatures and ultimate stress, are understandable. And now that we have talked a little about ductile and brittle materials, we will see what are ductile materials and what are brittle materials in detail. Ductile and brittle materials. Now, we've already seen a little bit about ductile materials in the previous sessions. And again, when we take the stress strain diagram for ductile materials, we can see that these materials again have a prominent elastic region and a prominent plastic region, wherein this plastic region again has yielding, strain hardening and necking. And if we see in this area, which is sigma PL, it's called the proportionality limit, after which the elastic behavior of the material comes to an end and the material slowly starts behaving like a plastic material. So after proportionality limit, we then have sigma Y, which is the yield stress. So this is the point where the material undergoes yielding, and as engineers we can already call this material going under failure. And next limit for us is the fracture stress, which is sigma F. Now sigma F can be seen below ultimate stress, and this can also be called as the region where material is definitely going to fail. And when it comes to ultimate stress, there is a sudden drop. So this is where the material snaps into halves. So basically, ultimate stress is the region where we get the failure without any indication. One thing which we have to notice within this diagram is that once the material reaches its yield stress limit, you can see that the progress of strain here is much higher than the progress of stress. But then again, when it has to reach to the ultimate stress, the value of stress keeps increasing slowly after it goes beyond the yield stress or yielding region. Now this is exactly why whenever we use the universal testing machine or UTM, we mainly consider the ultimate tensile strength, or you can say that the ultimate stress. So with that, we'll go to the stress strain behavior of mild steel, which is basically a ductile material. Here, if you can see in this graph, this is again a strain diagram for mild steel. So like how we saw in the previous graph, important regions are given here. The first one would be our elastic region, then there will be yielding, and then there will be necking, and then there will be fracture. Here again, if you can see, sigma PL, which is the proportionality limit, comes under 240, and then sigma Y, which is our yield limit, and that comes under 262. So we can say that very small elastic strain values can be noticed when compared to its plastic behavior. So if you can see here in the plastic behavior, it can go up to 0.380. At the same time, below the yielding limit, it is below 0.030. There is a lot of difference between the plastic and elastic region when it comes to strain. Next, sigma Y is the yield stress and is the highest stress that can be applied before yielding. Now we've already seen about this, wherein sigma Y is our yield stress. Third point, which is sigma U, that is the ultimate stress, and this is the highest stress that can be applied before necking or eventual failure. Now we have sigma u as 435, which will be our highest stress that has to be considered. Now the same way we have a stress strain behavior of cast iron, which is a brittle material. Also, we have to keep in mind that there are some unaccounted loading conditions which we can call as impact loading. So one main example for impact loading would be natural disasters, for example earthquake or tornadoes or hurricane hitting buildings, and in these times mild steel or materials like mild steel can undergo unaccounted loading, and while undergoing unaccounted loading, this region, which is from the yield stress up to the ultimate stress, this region can help withstand the unaccounted loading. So with that, we'll go to the next material, which is cast iron, and this is a brittle material, and for this also again we'll be seeing the stress strain behavior. So when it comes to cast iron or any brittle material like cast iron, the stress strain curve is something that looks like what we can see in the right hand side. So all this time the stress strain curves that we were seeing were loaded as tensile stress because ductile materials have very weak compressive properties. However, this material has both loads. One is the tensile and the second is the compressive load. If you can see here, it starts from the tensile load and then goes into the compressively loaded region. So we'll see that again. So in the right side, you can see there is a small curve that starts with the tensile loading, and then this curve gives you the yield stress, which is basically equal to fracture. So now that we've got the yield stress, we can say that it has reached its yielding. But we know that brittle materials do not have yielding, they just directly have fracture. That is because already we saw that brittle materials are materials that break without any indication. So here the yielding stress can actually be called as fracture stress, which finally results in the complete failure of the material. However, when it comes to compression, it is a completely different story. You can see that when compressive load is given, the graph keeps on going linearly, and then it goes approximately up to a value of 1000 until it reaches its compressive failure. Now from this graph, we can say that brittle materials are usually weaker in tension but stronger in compression compared to ductile materials. Also, in tension, the fracture is initiated at an imperfection or micro crack and the failure occurs rapidly. So like we saw earlier, the failure occurs in a snap, there is no indication. But in compression, the flaws and micro cracks basically close because we are giving inward stress and the material can withstand much higher stresses. And if we take stress strain behavior of concrete, which is again a brittle material, we can say that from the graph, the compressive strength would be up to 34.5 megapascal, and at the same time it has a very low tensile strength, which is approximately 2.76 megapascal. Now we know what a concrete is, and we also know that it can have lots of cracks or micro cracks inside, because we know that concrete is basically made of few different materials like sand, cement, and it's just a mixture of all these materials. Now these materials are mixed together and then it's solidified. These cracks and micro cracks are one of the very important reason for it to have a very low tensile stress or tensile strength. But when it comes to compressive strength, the difference is very high, and therefore concrete is widely used in many building structures. And also, to compensate for the substantially lower tensile strength of concrete, we reinforce concrete with steel rods, making it much more stronger in the tensile region as well. So now we can call concrete as a composite material, wherein the steel holds tensile strength and concrete holds the compressive strength. So theories of failure are primarily either stress based or strain based theories. Most of the strain theories work well with both ductile and brittle materials, whereas stress based theories might work with both types or it can be tailored towards one type of material. It is very important to understand that none of the theories can be always applied to a specific material. Now, the reason being, each material behaves either as a ductile or a brittle material, and the behavior is dependent on many aspects such as loading rate, temperature, chemical environment, forming, and shaping the material. However, we might use any particular theory, but finally, the point of highest normal and shear stress should be calculated first. And eventually, the principal stresses at those points should be estimated, as majority of the theories are based on this principal stress. Now, there are two theories, or we can call two strain theories, that are widely used, and these were introduced by Saint Venant and Beltrami. So now we'll go into the maximum principal strain theory, which was first given by Saint Venant. Now, this theory is dependent on the assumption that inelastic behavior resulting in failure is caused by a normal strain that is higher than the specified limit. The failure will be experienced by a particular part of the body that is subjected to any arbitrary state of strain at that instance when the normal strain reaches the limit. So basically, there should be a specific strain limit for a particular material. But if the normal strain is higher than the specific limit or the specified limit for that particular material, then the material will fail. Now, for a given body, a small part of this body can experience failure when there is arbitrary strain that this small part of the body undergoes, and this arbitrary strain also goes beyond the normal strain that has to be given. Next, failure can be predicted when any one of the principal strains resulting from any principal stress, which is sigma 1, 2, or 3, is the same or greater than the maximum strain that corresponds to the yield stress sigma y of the material in tension or compression. So basically, if the principal strain which is caused by any of the principal stresses is higher than the strain that is corresponding to the yield stress, then the material will fail. Now, this can happen either in tension or compression, and when it happens in tension, it is for ductile materials, and when it happens for compression, it is for brittle materials. Now, with that, the equation or criteria for not failing, you can see here it as sigma 3 minus nu into sigma 1 plus sigma 2 should be lesser than sigma y, which is the yield load or yield stress. Now, we shall do a small derivation in the whiteboard and then arrive at the final equation. Now, assuming we have a triaxial loading, so we'll write triaxial loading. Now, with triaxial loading, we'll have sigma 1 or sigma x, sigma y, and sigma z with triaxial loading. Now, we know that Young's modulus is equal to E. Young's modulus is given as E, and Poisson's ratio is given as nu. Let us take three principal stresses, like how we took in the previous sessions. We had principal stresses and maximum principal stresses. So with that, we'll take three principal stresses, sigma 1, sigma 2, and sigma 3. Now, if we have principal stresses, we'll also have principal strains. So for that, we can take epsilon 1, epsilon 2, and epsilon 3. Now, assuming that in the principal strains which we took, assuming that epsilon 1 is greater than epsilon 2 and epsilon 2 is greater than epsilon 3. By substituting these assumptions within the generalized Hooke's law. So this is going to be a generalized Hooke's law. And by taking 1 by E as a common variable, and we also have nu as common variables for these two equations. So sigma 1 minus nu of sigma 2 plus sigma 3. Now we can write the same for epsilon 2, which is 1 by E into sigma 2 minus nu sigma 3 plus sigma 1, and same way epsilon 3 is equal to 1 by E into sigma 3 minus nu into sigma 1 plus sigma 2. Now we got these three equations, and when the specimen is undergoing uniaxial tension, the strain at yield point is given as epsilon yt. So this can be taken as strain at yield point. So I'm going to write it as yield point strain. And from Hooke's law, we can say that the yield point strain, which is epsilon yt, can be given as sigma yt divided by E. E is the Young's modulus. Now, we saw a statement before we came inside the derivation, and this was the statement which was given by Saint-Venant. Now, before we came into the derivation, we saw Saint-Venant's theory. From the theory, what we understood is that if epsilon 1 is greater than or equal to epsilon yt, which is yield point strain, then the material undergoes failure. This is what Saint-Venant has given. Now, from that, we can use this equation and create a final equation, which is epsilon 1 is equal to 1 by E sigma 1 minus nu into sigma 2 plus sigma 3 should be greater than or equal to sigma yt divided by E. Now, we know clearly that sigma yt divided by E is from this, and epsilon 1 is from here. Now with that, by reordering the equation, we can cancel out E, and the reordered equation will be sigma 1 minus nu of sigma 2 plus sigma 3 should be equal to or greater than sigma yt. And here, so yt is when there is yield at tensile loading, and at the same time we can call it yc when there is a yield at compressive loading. So the equation can also be written as sigma 1 minus nu into sigma 2 plus sigma 3 should be greater than or equal to sigma yc, and this is for yield at compressive loading. The next type of strain theory is our total strain energy theory. This is also called as Beltrami's or High's energy theory or strain energy theory. Now this theory is applicable to both types of materials, which means it's applicable for both ductile and brittle materials. Now the theory predicts failure or inelastic action at a point when the strain energy per unit volume exceeds a specified limit. Failure can be predicted when any one of the principal strains is the same or greater than the maximum strain that corresponds to the yield stress sigma y of the material in tension and compression. Now basically, if we take any one of the principal strains, and if this principal strain is equal or greater than the maximum strain, so this maximum strain is something that corresponds to the yield stress, which is sigma y. Now if this principal strain which we have taken is greater than the maximum strain, then we can say that there's a failure of that material. And like how we saw previously, again this material is when it is in tension or compression. Now the given equation for not failing says that sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3 should be lesser than the square of sigma y, or the square of the yield stress, so that the failure does not happen. Now to derive this formula, we'll again jump to the whiteboard. Now, like how we saw earlier, again we are taking a triaxial loading, and we have three stresses: sigma x, sigma y, sigma z, and the principal stresses can be given as sigma 1, sigma 2 and sigma 3, and the principal strains can be given as epsilon 1, epsilon 2, epsilon 3. These are the corresponding principal strains after we give the principal stresses. We have Young's modulus E and Poisson's ratio nu. Now from the generalized Hooke's law, we have these values for epsilon 1, epsilon 2 and epsilon 3. With these values, we will try to construct the total strain theory given by Beltrami or Hooke. So the total strain theory involves strain energy. So we can give strain energy as U, which is equal to Uy. Here Uy is the strain energy that we get for yield strain. So yield strain is the corresponding strain when the material undergoes yield stress. So from the strain theory, we have 1 by 2 into sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3 is equal to 1 by 2 sigma y epsilon y. And we also have the generalized Hooke's law, wherein we have the values for epsilon 1, epsilon 2 and epsilon 3, and we'll substitute these values within this equation. And after substituting, we'll get something like this. So sigma 1 into sigma 1 by E minus nu into sigma 2 by E minus nu into sigma 3 by E plus sigma 2 to sigma 2 by E minus nu into sigma 3 by E minus nu sigma 1 by E plus sigma 3 into sigma 3 by E minus nu into sigma 1 by E minus nu into sigma 2 by E. While simplifying, we'll be negating, or we'll be taking out E as common and nu as common, and we'll get a final equation which is something like this: sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu to sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 is equal to sigma y square. Now failure happens when this equation is equal to sigma y square, or it's greater than sigma y square. So basically greater than or equal to. And we can stop failure when the value which we get from this equation is lesser than sigma y square. Yield theories for ductile materials. So these theories that we'll be looking into from this point are specifically for ductile materials. They can be used for brittle materials, but they do not work always. So these theories are mainly dependent on the behavior of ductile materials. So during designing a load bearing structure using a specific material, it is important to place an upper limit for the stress value which will define the material's failure. So basically, engineers will always place an upper limit, not based on a random selection but based on calculations of the end material. So this failure is usually specified at the point where yielding is initiated, which is sigma y, and therefore for ductile material the failure is specified at that point. And then we have a buffer which can also be called as a cushion time, which will lead to ultimate stress. However, in brittle materials, this failure is specified by the point where the fracture is experienced directly. So basically it's a snap without any indication. Now, like we saw previously, we will be looking into theories of failure for ductile materials specifically that are used in general engineering practices. And the most common failure theories for ductile materials involve Tresca failure theory or maximum shear stress theory, and the second one is Huber-Henke von Mises theory or maximum distortion energy theory. So the first one we will be looking at is the maximum shear stress theory, which is also called as Tresca theory. Now, a ductile material in which one of the simplest examples being steel usually fails through slipping. Now this is a very interesting phenomenon. The phenomenon can be easily seen on a highly polished thin strip that is subjected to tensile loading. The edges on the slipping plane, which are visible to the surface of the tested strip, are known as Luder's lines. So if you can see on the right, we have the Luder lines on the mild steel strip. So basically, when this mild steel strip is under tension, these lines will come up and it's usually 45 degrees to the plane of the shear stress, and these lines are the main reason behind slippage. Because these lines are at an angle and there is a shear stress because of that, we need to calculate the shear stress based on the state of stress based on loading. Now the yield stress of that element is sigma y, and the maximum shear stress can be calculated from the Mohr circle as tau max is equal to sigma y by 2. So furthermore, through stress transformation, we can calculate that the shear stress acts at a 45 degree angle respective to the principal stress planes. Since the plane of shear stress falls where the Luder's lines are, the material fails by shear stress. And if we do the calculation, we will see that the shear stress acts at a 45 degree angle and will be transferred to the principal stress plane. And since this angle coincides with that of the Luder line, the material will fail by shear stress. Now Tresca proposed the maximum shear stress theory, and which is also called as Tresca yield theory, with these concepts. Coming to the definition, so regardless of the loading type, the yielding of a material is initiated once the absolute maximum shear stress reaches the value of that shear stress that results in the yielding of that structure under axial loads only. Therefore, to limit failure, it is important to ensure that the absolute maximum shear stress is lesser than or equal to sigma y by 2. Now, we know that we got this value from the Mohr circle, and in terms of plane stress, the absolute maximum shear stress can be represented in terms of principal stresses sigma 1 and sigma 2. If both the principal stresses have same sign or orientation, tensile or compressive, the failure of fracture occurs when the absolute maximum shear stress is lesser than or equal to sigma 1 by 2. However, if the two principal stresses are in opposite direction, then the failure occurs when the absolute maximum shear stress is lesser than or equal to sigma 1 minus sigma 2 divided by 2. So based on the previous two equations, we can get these mathematical formulas as our final equations in the maximum shear stress theory. With that, we'll move on to the next theory, which is maximum distortion energy theory or Huber-Henke von Mises theory. So this theory was initially given by Huber, and then it was then modified by Henke and von Mises following Huber. So a material is known to experience deformation when an external load which results in energy storage throughout the volume. Here, strain energy density is defined as this stored energy per unit volume of the material. Now in case of uniaxial stresses, the strain energy can be defined as U equal to 1 by 2 into sigma E. Now we use this strain energy to figure out the derivation for Beltrami or Hayes theory. Now when we take triaxial stresses, due to contribution of each principal stress, the strain energy density can be given as U equal to 1 by 2 sigma 1 epsilon 1 plus 1 by 2 sigma 2 epsilon 2 plus 1 by 2 sigma 3 epsilon 3. And from the stress theory or from the strain energy density, the Hooke's law can also be given as U equal to 1 by 2 E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu, where mu is the Poisson's ratio, sigma 1 sigma 2 plus sigma 1 sigma 3 plus sigma 3 sigma 2. Now what we have done here is we have substituted the generalized Hooke's law equation in place of epsilon 1, epsilon 2 and epsilon 3, and then we have arrived at this solution. So this equation can be observed to be in two distinctive parts, one being energy needed for volume change and other being shape change. Here if you see, in the left hand side there is energy change which is U, and in the right hand side there is shape change. Interestingly, the energy stored in the element due to volumetric change is caused from average principal stress that causes equal principal strains. Now the remaining portion of the stress equation results in energy for shape distortion. Generally, materials do not yield under a uniform hydrostatic load or average stress. Therefore, Huber proposed that in ductile materials, yielding will be visible once the distortion energy per unit volume is more or equal to the distortion energy of the same material under tension. So from whatever Huber proposed, we can obtain an equation with that, which is sigma average, that is equal to sigma 1 plus sigma 2 plus sigma 3 by 3. Now substituting sigma average in the previous equation which we saw, we will get a modified version of the strain energy equation, which is U equal to 1 plus mu by 6E into sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square. Now we know that in case of plane stress, sigma 3 is equal to 0. Sigma 3 is equal to 0 because it's a biaxial case. Therefore, substituting sigma 3 as 0 here, we get U equal to 1 plus mu by 3 into sigma 1 square minus sigma 1 into sigma 2 plus sigma 2 the whole square. So finally, for uniaxial tension, where we can take sigma 1 as sigma y and sigma 2 sigma 3 equal to 0, we will get U equal to 1 plus mu by 3 into sigma square y. So this is the simplified version of the previous equation. Now if we can see here, we can always equate sigma y square to sigma 1 square minus sigma 1 sigma 2 plus sigma 2 the whole square. Therefore, from maximum distortion energy theory, wherein U equal to Uy, we get sigma square y is equal to sigma 1 whole square minus sigma 1 sigma 2 plus sigma 2 the whole square. When we take this equation in a mathematical form, we can say that it is an equation of an ellipse. Therefore, if the material is stressed enough to have a point outside ellipse, the material will fail. Now, one thing we have to note here is that comparing the two, it can be noticed that both the theories give similar results. So because both the Tresca theory and Huber-Henke-von Mises theory play in the same field region and play with nearly the same variables also, we can say that it gives similar results. And the stress magnitude from both the theories show exact same values when the principal stresses are same. But when it comes to pure shear, the theories can be observed to have a large discrepancy, which is it can be calculated that, experimental calculations says that Huber-Henke-von Mises theory gives 15% more accuracy compared to Tresca's theory. The next mode of failure criterion will be failure criterion for brittle materials. Again, we have few theories of failure in brittle materials. Now, the general theories that we use in engineering practices are maximum normal stress theory by Rankine and Mohr's failure criteria. We will be seeing only these two criteria. Now, under maximum normal stress theory by Rankine, You can see that brittle materials tend to fail suddenly under tensile loading. It undergoes fracture without showing any yielding. So basically, without giving any indication, the brittle materials tend to undergo failure. Also, the fracture is seen only after the material reaches ultimate tensile stress. Now, ultimate stress is also known as ultimate tensile strength, which is often abbreviated as UTS. Now, it is called ultimate tensile strength because it is being loaded in tension, and therefore the stress of the equivalent strength is given as ultimate tensile strength or ultimate tensile stress. And on the right side you can see there are some failure types. So the first one is failure of brittle material in tension, and the second one is failure of brittle material in torsion. Now if you can see in this diagram or in the drawing which is in the right side, in brittle materials, due to torsion there is a sudden snap. So this material doesn't undergo any kind of strain hardening, necking or anything, it just snaps. The same thing happens when it undergoes tension also. There is just a indicationless snap of the material. But when we take ductile materials, for example if we take materials like polypropylene, it has a very long necking time and then only it fails. But like we saw earlier, for the brittle materials, after the first crack initiates, the material will break away very fast when it is in tension. Now brittle materials also experience tensile fracture in torsional test because the plane of fractures is usually at 45 degree with respect to the shear plane. So if you can see here, the plane of fracture has been drawn which is at 45 degree angle, and this is where the shear force is also highest, and that is exactly where the failure occurs or the fracture occurs. Now we can prove this with the previous theory wherein we saw Luder lines. So Luder lines occur at 45 degree angle when there is a shear stress is given to the material. Now with that we can confirm that when the brittle material is undergoing torsion, it fails when it reaches 45 degree. Now it has been proven through experiments that under torsional loads, the material's overall strength is minutely affected by the presence of the associated principal compressive stress. Therefore, the stress that results in fracture during the normal tensile test is same as that needed for the material to fail under torsional loading. So from this statement what we can understand is, when we take compressive stress, they don't really result in significant failure. It is usually the tensile load and the associated tensile stress that results in actual failure of the material. So under tensile loading, the failure that is observed is actually the stress that results in fracture of that material system. So therefore the theory is primarily based on principal tensile stress, and it states that it fails when the principal tensile stress is equal or higher than the ultimate normal stress of the material that is undergoing tensile loading. Now this ultimate normal stress of the material is defined by ultimate tensile stress because the action of compressive stress there is negligent. Now for this theory, a chalk is a good example of a material that experiences similar failure. Thus, under plane stress, the material should satisfy modulus of sigma 1 is equal to the ultimate stress and modulus of sigma 2 is equal to ultimate stress, which is sigma ULT. Now in the right side we can see that sigma ULT is marked in the coordinate system which has sigma 1 and sigma 2 as its horizontal and vertical axis respectively. Now after marking minus sigma ULT and positive sigma ULT, we can build a region, and with this we can say that the material fails when the stress coordinates sigma 1 sigma 2 or sigma 1 comma sigma 2 falls on the boundary or outside of the shaded area as illustrated. Now if after calculations the coordinates of sigma 1 and sigma 2 falls on the boundary of this shaded region, or outside the boundary of the shaded region, then it means that the material is undergoing failure. So this is given as the maximum normal stress theory. Next, we'll move on to the Mohr's failure criterion. So some specific materials have different properties under compression and tension loadings. Therefore, a specific criterion is required to predict failure in similar materials, which is based on the Mohr circle and is known as Mohr's failure criterion. So to successfully apply the criterion, it is required to perform 3 tests. These 3 tests will be used to apply the criterion, which is the Mohr's failure criterion, and then find out the failure range. Now those 3 tests are uniaxial tensile test to get the ultimate tensile stress, uniaxial compressive test to get the ultimate compressive stress, and torsion test to get the ultimate shear stress. Now the Mohr circle for each of these conditions are plotted. If you can see in the right side, 3 circles are plotted and the common regions are taken out of those 3 circles. Now this is the common region that has been created, and a failure envelope is created within the common regions of the 3 circles. That is what we discussed before. And if the plane stress condition of a particular state of stress makes a tangent to the envelope or lies outside the boundary, it will result in material failure. So like how we saw in the previous mode, wherein we had a square, and if the coordinate points resulted in the boundary of the square or outside the boundary of the square, we said that it will undergo failure. Same way, we have the common region here, and if the plotted line or plotted points are in tangent with the boundary of this region or falls outside of this region, then it means that the material is undergoing failure. Now the 2 materials which we saw were mostly based on stress, and we didn't come across many equations because both these criteria have to fall under a region of coordinate system, and in which we will be using the Mohr's circle to depict the failure. So with that, we have come to the end of the failure theory. Now we will see some examples relating these failure theories. So we can see an example here, which is the solid steel shaft has a diameter of 1 inch and yield stress of 36 ksi. Yield stress is sigma y. Now we will have to determine whether the loading causes failure, and this we have to determine with 2 failure theories. One is the maximum shear stress theory and the second one is the maximum distortion energy theory. The first one is basically Tresca theory and the second one is the Huber theory. Okay, first is first, we will have to note down the given values. So the first value we will be noting down is P, which is the axial stress, and that is 15 kip. Next, there is torsion involved, which is equal to 3.25 kip inch. We know that the diameter is equal to 1 inch, therefore radius will be equal to 0.5 inch. Now it is important to figure out the cross sectional area to get values for the force, which is stress is equal to force by area. Now for the cross sectional area, CSA, A equals pi r square, as this is a tube and cross section is a circle, which will be equal to 3.14 into 0.5 the whole square, and that will be equal to 0.79 approx inch square. Now we know that torsion loading influences torsional stress and axial loading influences axial stress. This influences axial stress. We saw about torsional loading in our previous sessions, and the torsional loading will give us torsional stress. Now when we take sigma x, which is the axial stress or normal stress, we can say that it's going to be P by A, and that will be equal to 15 by 0.79, which is equal to, after calculation we will get 19.1 ksi. In same way for torsion, we already know the formula for torsion. So tau xy will be equal to T into C by J, where T is our value of torsion, C is the maximum length at which this torsion is happening, and here the maximum length is the radius because the torsion is happening in the surface, and for us the radius is 0.5 and J is a polar moment of inertia. We know the formula for polar moment of inertia also, even that we have seen in the session where we have talked about torsion. So by substituting these values, it's going to be 3.25, which is the torsional value, into 0.5 divided by pi by 2 into r to the power 4. We know that the value of r is 0.5. So with that, tau xy will be equal to 3.25 into 0.5 divided by pi by 2 into 0.5 the whole power 4. So tau xy will be equal to 16.55 ksi. Now although these values are given here, if you can see here, these values are already given here, but just as a refresher, we have again gone through these equations. Now if you can see here, the axial stress is acting inwards. Because it is acting inwards, we can term this axial stress as sigma x is equal to minus 19.1 ksi. Because there is a clockwise torsional force or clockwise torque, we can say that our tau xy or our shear stress is positive. Now next we will have to figure out our principal stresses. So for our principal stresses, sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus or minus root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square. Now here we only have axial loading in the x-axis. There is no y-axis loading. So we can say that our sigma y is equal to 0. So if sigma y is equal to 0, this value is equal to be 0 and this value can also be given as 0. Sigma 1 comma 2 is equal to minus 19.1 by 2 root over minus 19.1 by 2 the whole square plus 16.55 the whole square. Now after simplification, we'll get sigma 1 as 9.56 ksi and sigma 2 will be equal to minus 28.66 ksi. Now that we've got the values for sigma 1 and sigma 2, we can go ahead and calculate the fracture criteria. Our first criteria here will be the maximum shear stress theory. So maximum shear stress theory. So in the maximum shear stress theory, we came across few conditions. So these conditions were when sigma 1 and sigma 2 are of same signs and sigma 1 and sigma 2 are of different signs. Now by these conditions, we can see that we have different signs in sigma 1 and sigma 2. So according to that condition, we have to satisfy modulus of sigma 1 minus sigma 2 to be lesser than equal to sigma y. And in the question or in the problem statement, it is already given that our yield stress is equal to 36 ksi. Now calculation of sigma 1 minus sigma 2 modulus should be lesser than or equal to sigma y. So substituting values for sigma 1 and sigma 2, 9.56 minus 28.66 should be lesser than or equal to 36. And after calculation, we get 38.22 less than or equal to 36. Now with this, we can say that shear failure will occur. Now for this given torsion and given load, the material cannot withstand shear failure. We should also note that shear failure is the most prominent failure than any other failure in any material. So now we'll go to the next type of failure. The next type of failure criterion is going to be our maximum distortion energy criteria. So by this criteria, the formula given was sigma 1 square minus sigma 1 into sigma 2 plus sigma 2 square should be lesser than or equal to sigma y square, wherein again sigma y is 36 ksi, and that's given. So substituting those values here, which is 9.56 the whole square minus 9.56 into minus 28.66 plus minus 28.66 the whole square should be lesser than or equal to 36. Okay, this is 36 square. So after simplification, we get a value of 1187 lesser than or equal to 1296. So here we can see that the material does not fail as it satisfies the equation. Now when we were going through the distortion energy criteria, we also saw that the distortion energy criteria has 15% better results. So we'll give distortion energy criteria has 15% better results than the maximum shear stress criteria. So with that, we can conclude that the material does not fail because usually DEC or the maximum distortion energy criteria gives us better results. So with that, we come to the end of this session, and this is the last session, which is our failure criteria. And in this session, we learnt about ductile and brittle materials. We came across a different stress strain relationship for ductile and brittle materials. We saw different types of failure yield criteria for both ductile and brittle materials separately, and these theories were based on either stress or strain theories. With this, we conclude our Strength of Materials course. Thank you.